participate to keep this conference dynamic and for it to prove effectual in its goal as a platform to explore and share knowledge. Without delay, let us start the third session of ICMPMA and the first session of the day. The topic for today's conference is materials. To chair the session, we invite Professor P.P. Pradyumnan, who is a senior professor at the Department of Physics, University of Calicut. He has 25 years of teaching experience in the department. He completed his BSc in Physics from SN College, Kannur, and MSc and PhD from the School of Pure and Applied Sciences, MG University, Kottayam. He is the recipient of CSIR, UGC, and GRF. He has over 27 years of research experience in solid-state physics, semiconductors, material science, crystal growth, thin films, nanomaterials, polymers, multiferroics, ceramics, nanomagnetic materials, etc. He is also the visiting professor at Waseda University, Tokyo, Japan. He has several research projects to his credit and has guided more than 10 PhD students. Currently, his research interests include thermoelectrically important thin films and bulks, electrical and magnetic properties of thin films, semiconductors and its properties, synthesis of multiferroic compounds and its property studies, growth of inorganic, organic, biologically important crystals, fabrication of nanocrystalline photovoltaic films, TCO thin films, nanocarbon powders, multiferroic materials, nanomaterials, etc., natural polymers characterization and electric property studies, and triboelectricity. He has published about 86 research publications in journals of international repute, 14 book chapters of proceedings, and has authored 2 books. Dear sir, we are honored to have your brilliance here with us today. We cordially invite you to start the session. Professor Pradyumnan.
Hello, good morning.
Yes, sir, we can hear you.
Good morning to all. Am I audible?
Good morning, sir. Yes, sir, you're audible. Sir, we can see you, you're audible.
Hello, Pradyumnan sir.
Am I audible?
Sir, you are audible, sir.
Am I audible now?
Yes, sir, you're audible.
Yeah, okay. I think I can start now.
Yes, sir, you can start.
Okay. Good morning to all. First of all, I thank the organizers for giving this opportunity for chairing the session of International Conference ICMPMA 2022 Energy Materials session. Today we have one plenary talk and invited talk of 4. Okay. First talk, plenary talk, is doing by Professor Aldrin Anthony, and is from Cochin University of Science and Technology. And his plenary talk is on transition metal oxides and two-dimensional materials for selective charge extraction in silicon solar cells. When we discuss about him, his biography is very, very rich. And Dr. Aldrin, first of all, I welcome Aldrin Anthony for this conference. And now I can say something about his biography. Dr. Aldrin Anthony is an associate professor at the Department of Physics and also honorary director of the Center of Excellence in Advanced Materials at Cochin University of Science and Technology, Oxide. He received his MSc in Physics and PhD from Cochin University of Science and Technology. He was a postdoctoral fellow of INEA, Italy, and research scientist at the Bombay Group D Energy Solar of the University of Barcelona, Spain. He was a senior scientist at IIT Bombay from 2012 to 2019. Dr. Aldrin was the independent director of the startup company Renewable Green. Dr. Aldrin has received international postdoctoral fellowship by ICS, UNIDO, ICTP, UNESCO, and Juan de la Sierra. He was the Distinguished National Solar Science Fellow of Ministry of New Renewable Energy, Government of India. Dr. Aldrin has over 20 years of research experience in material science and works extensively in state-of-the-art solar cell fabrication. His current research interests are in low-cost silicon heterojunction solar cells, agri-photovoltaic, biosensors, two-dimensional materials, and neuromorphic computing. He was supervised 4 PhD theses and has published more than 50 research papers in peer-reviewed journals. He has 5 patents to his credit. He is also a consultant to different equipment manufacturing companies for product design, fabrication, and process development. With this introduction, I invite Professor Aldrin for his talk.
Thank you, Pradyumnan sir, for a nice introduction. And also I'm thankful to the organizers of the conference at ICPMA for giving me this opportunity to give a plenary talk in this session, especially in this field of energy materials. In this field, which I've been working for more than 2 decades. And especially thank Jin Jos, who is the conference chair of the international conference. And I'm just directly going to the presentation. Whether my screen is visible now.
Yes, sir. Yes.
Is it full screen?
Yeah, yes, it is.
Great, great. Thank you. So shall I start? Without wasting much time, I'm just directly going into my talk. It's 9:42. Okay, so I hope it will be like some 35 to 38 minutes. I hope I could conclude in that time. And okay, my topic, the title of the talk today is Transition Metal Oxides and 2D Materials for Selective Charge Extraction in Silicon Solar Cells. So the title seems to be a very lengthy one, but I'm just trying to say something about a very simple, if I'm say, is one part is a very low-cost solar cell fabrication method, and other one is a challenging solar cell fabrication or futuristic solar cell fabrication method. So these are the 2 parts, and I'm mainly focusing on the low-cost fabrication of solar cells that we could do even in our lab. So this is the outline of the seminar. The first part, I'll be just giving an introduction, then carrier selectivity, what do you mean by the carrier selectivity hetero contracts, then different types of hole and electron selective contacts, and then we'll go to a heterojunction, a full hot heterojunction solar cell. Sorry for the typo, that is a hole is written as HALL, it's HOLE, hole transport. And then the last part is a 2D TMDC, that is a 2D transition metal dichalcogenide as a carrier selective contact for silicon. So So when you talk about this energy materials in this conference, we have to think about why the energy materials are of importance. And this is, one of the things that we are already in Kerala, we are experiencing due to the global warming scenario. That is, we can see a lot of the landslides are happening and the erratic weather conditions and unprecedented rains, the floods, and all this because of the global warming, and which is actually caused by the burning of fossil fuels. And our human civilization is depending a lot on this type of fossil fuels for more than 200 years. And from the start of industrial revolution, we have been extensively using these fossil fuels for our there's an exponential increase in the fossil fuel usage, and that is leading to a carbon dioxide emission. So if you look into the natural resources that we are limited is with approximately we have something around 150 years for reserve for coal and 40 and 65 years for crude oil and natural gas reserves that we have. And so what's the environmental impact by this fossil fuel usage that is happening all around is basically the carbon dioxide emission. And when the carbon dioxide emission takes place, as you can see in the curve, the carbon dioxide emission from 1800, it started increasing exponentially, and it is something around 450 ppm carbon dioxide equivalent in our atmosphere. And it has been widely accepted now. This theory of the global warming is basically due to the carbon dioxide emission, and that's the main reason. And that leads to the erratic weather patterns and footprints. And that is one of the reasons all the countries are joining together and trying to control this global warming. And our aim is to hold the temperature rise within 2 degrees C by 2050. Initially, it was planned to be like 1.5 degrees centigrade above the temperature during the Industrial Revolution, and that is in 1800s. But now, realistically, what we are thinking that we may not be able to reach that 1.5 degree rise in temperature. Now, already it is something around 1.1, 1.2 degree rise in temperature. So if you are going like this in the present consumption of fossil fuels and the burning of fossil fuels, our temperature, the global temperature will rise by 2 degrees by 2050. So at least we have to hold it by 2 degrees. So even if you use by like increase by 2 degree rise, the seawater or the level of water will rise by around something around 30 centimeter. So this is something of concern for all the global life or our normal way of life. And it is going to affect not only humans, it's also going to affect all class of life organisms in this earth. So this is the major concern that we need to move on to something renewable energies. And that is, if you look into our energy usage in India, we have, if you compare Kerala and India, in India, we have something around 62% of our major electricity generation is from coal. And with regard to the Kerala, it is only 23%, and Kerala we are having more depending on hydroelectric power, and it is only 70% is based on hydroelectric power. And if you look into the renewable energy scenario, so India, we are having 23% of total production of electricity is through renewables. And even in the renewables, 10% share is from the solar. And Kerala is lacking far behind the other states in India, and we have only like 5% in the total share of electricity generation in the state. And so why is solar energy? That all these things, but what I just highlight only 2 points. This gives a chance for an individual to generate his own energy at one's own place of choice. So whatever energy that we need, that we could generate in our own home and then use it. So why to depend on the grid or other energy sources? So a sustainable energy scenario is to be implemented or is to be raised here for the betterment of our planet. So I'm going to the physics or the basic physics of solar photovoltaic technology. And when you talk about this energy materials, and the most important thing which comes into mind will be always a solar powered power generation. And when you say about solar, it also involves a lot of the small hydropower, and also because the wind is also by the solar activity. So wind power, everything is, these things are related with the solar energy. And so specifically, when you say solar photovoltaic technology, that is, you are converting solar light into electricity, right? So basic things you know, but I'm just trying to give a introduction. So then I could move on directly to what I am trying to say about the low-cost solar cells. So the conventional, there are two types of solar cells. One is, we call it as a crystalline silicon solar cell, which is given on the left, and the other one is a thin film solar cells. Crystalline silicon solar cells uses a silicon wafer of a silicon wafer of 180 micrometer thickness at the industrial scale. And can anyone tell me where is this this pen. Okay. Okay, this is like a crystalline silicon solar cells where you have a p-type crystalline silicon, and then you will have a doped n-type crystalline silicon over the top, and that is a normal crystalline silicon solar cells is made. And this is done by using thermal diffusion of crystalline silicon wafer, and the other one is what we call as the thin film silicon solar cells or thin film solar cells, and that is basically on any substrate. It can be on a glass, it can be on a metallic foil, or it can be on plastic substrates. So a lot of flexibility is there for thin films, and the material used is only 1 to 3 micrometer. So that's a major difference. But if you compare the efficiencies, crystalline silicon solar cells are far high efficient materials. And these are the different types of photovoltaic cells, generation of photovoltaic cells. Basically, you can say about like 3 type of particular type of photovoltaic technologies: inorganic, organic, and hybrid. And in inorganic, it comes the elemental or silicon solar cells, which still further into crystalline and the thin film solar cells. And the recent ones, which are of major interest, is what they call as the perovskite solar cells, which is of current interest, and a combination of silicon and perovskite solar cells, one over the other, that we call it as the tandem solar cells, are of primary importance at this moment, and it has reached something efficiencies very close to 30%. And so there is a limit. If you are having a solar cell, it's a PN junction device normally, and in a PN junction device, but there will be a maximum efficiency a solar cell can have, because this depends on, and this is actually, it was derived in 1967 by Shockley and Kaiser, and the maximum efficiency of a solar cell with regard to the solar spectrum in what is available in the earth is 33.7%. So that is the maximum efficiency a solar cell can have. That is, if a light is coming, 33.7% of light has been converted into electricity. And that is for single junction. If it is a double junction, it will be 44%. And if it is an n number of cells, then it can be like up to maximum 66% of efficiency it can have with a solar cells. And the structure of a crystalline silicon solar cell consists of a p-type wafer, like 180 nanometer, and then you will be forming an n-type crystalline silicon over the top of p-type silicon by thermal diffusion. And once a thermal diffused p-n junction is formed, then when you irradiate with a light, then light is absorbed by the solar cell, and it will create electron hole pairs. And what will happen when it is electron hole pairs are formed? The electron or the hole, that's the white one I am representing as a hole, will move to the bottom, and the electron will move to the up, to the n side. And then electron will move laterally through this crystalline silicon, n-type silicon, and it will be collected at the contacts. And this is a type of curve that normally usually get when you take the characteristics of a solar cell, and this we call as the IV characteristics of a solar cell. And this blue one is the dark characteristics, and the red and green are the illuminated characteristics. So if you increase the light, if you increase the intensity of the light, then the number of photons falling on the cell increases, and that increases, in effect, increases the efficiency or increases the current in the device. And that is the basics of a solar cell. And this will be the normal structure of a solar cell. You have a P-type silicon, and over that an N-type thermally diffused silicon. And this diffusion is carried out at a very high temperature of something around 900 degrees centigrade. And then there will be another process of silicon nitride, which is actually a dielectric layer and also for an anti-reflection layer. And it serves an additional purpose of passivating the material. And passivation means if you are putting a material over the top, there will be a lot of dangling bonds on the silicon surface. That is the lone pair bonds of silicon, which will act as recombination centers. And this lone pair bonds can be passivated by putting this dielectric silicon nitride. And over that, will be having an contacts. And this is the structure of a normal crystalline silicon solar cells that you could see on the rooftops or the solar module installations. And if you look into the band diagram, this is the P-type wafer, and this is the N side. And when you have an N plus side, there is a band bending, and the electrons here can easily move to this side, and the holes will be prevented to come to this N side. And here on the other way, that since you are having a P plus layer on the back side, the P plus layer on the back side, and the P plus layer on the back side, which gives a band bending upwards, which prevents electrons from collecting onto the contacts here. And the holes can easily move to this side. And this we called as a back surface field for a crystalline silicon. So keep in mind, this is a structure normally used to have a thermally diffused p-n junction. And then you have a P plus layer at the bottom, and to just have a carrier selectivity on the back side like this. And here electrons can move easily, and the holes will be blocked here. This is the normal concept of a crystalline silicon solar cells. Now let us see how it is different when you go for a new novel type of crystalline silicon technologies. So if you look into the market share of the crystalline silicon, the 95% of the market share of the crystalline silicon is by the crystalline silicon, and only 5% is by the thin film silicon. And if you compare the different efficiencies, you can think about three different type of crystalline silicon modules. One is of moderate efficiency, that is 19 to 22%. And in that you can say initially there was a polysilicon or aluminum BSF type of solar cell, which I showed you earlier, that can have maximum efficiency of 18%. But all this type of PERC solar cell, which is recently being installed in Kerala, most of the modules which are being installed in Kerala are by the PERC, PERC passivated emitter rear contact solar cells, and they are having a moderate efficiency of 19 to 22%. And then we can say about a high efficiency solar modules, and they are like bifacial solar cells or a TOPCon, that is tunnel oxide passivated contacts. And the third category, super high efficiency solar cell, there are new concepts which are still translating into production. And they are polar solar cell, silicon heterojunction. Silicon heterojunction is still there, but the cost is really very high. And they have the world record of 26.7% efficiency. This is for a 26.3 for a silicon heterojunction, and the latest highest efficiency is 26.7 for a interdigitated back contacted concept, that is 26.7. And so we are thinking about some low-cost methods which falls here, but having the efficiency, a moderate efficiency, but with a lesser cost. That's what we are trying to say. So, and that carrier selective contacts comes in this particular area. So that is what I'm going to talk about. That is a carrier selective contacted solar cells. And they have the same potential as heterojunction solar cells, but we have to improvise a lot for technologically improve the performances. And so if you look into a aluminum BSF versus a carrier selective solar cell, you have a crystalline silicon solar cell, a crystalline silicon here, one side will be N plus diffused, and other side will be P plus diffused. And this is the band structure which I have shown earlier. And this is a thermally diffused p-n junction. There will be a built-in electric field that will be formed, which acts as a driving force for the charge carrier separation. And in the P plus region, the carrier selectivity and ohmic contact, and normally it's a p-type crystalline silicon wafer is used. So this is how a charge separation occurs in a crystalline silicon solar cell. And now we look into a carrier selective contacts. That is, you take like an N-type silicon. So then itself, there will be a lot of marginal difference. It happens. That is, if you're having a P-type crystalline silicon, it is having a lot of defect states compared to N-type silicon. So N-type silicon is having less bulk defects compared to the P-type silicon because of some boron-oxygen complex formation in the P-type silicon. So normally the bulk lifetime of the minority carriers in N-type crystalline silicon is high. So that's why N-type crystalline silicon solar cells can achieve higher efficiencies. And what we try to do is we will give two contacts on both the sides. One is, this contact, what we called as a hole selective contact, and the other contact we call as an electron selective contacts or electron selective layer or a contact. So what happens is when you put this hole selective contact, this gives a barrier for the electron to move in this direction, and it selectively passes only the holes to move in this direction. In the other side, right side, it gives a facility for the electron to move to the other side, but it blocks all the electrons, all the holes that are coming to the right side. So this effectively works in a selectivity on both the sides due to an asymmetry, and it gives a band offsets, let's say. So it works with the band offsets, a right band offsets for electrons here and a band offset for holes in this side. And that we call as a hole transport layer or electron transport layer for a crystalline silicon solar cell. And so this is a heterojunction concept. And there is an asymmetry in the band bending happens because of this band offsets. And then there will be like the band offsets, the delta EC for the conduction band offset, and the delta EV that we can call a valence band offset. So this is delta EV and this is delta EC. And there are high work functions. And if you look into what are the type of materials which are used for HSL and ESL, high work function materials are used normally for the HSL, and the low work function materials are used for electron selective contacts. So this is how a high work function metal works. So if you are a high work function metal, when the two materials are joining together and when the Fermi levels get aligned, then it forms a huge band bending occurs in the silicon, which prevents the electron to move in this direction. So band offset forms on this silicon HSL interface, and it blocks the electrons and it can only pass holes in this direction. And there will be an inversion layer is formed, and from here electrons can move into this layer through the contacts by tunneling or thermionic emission. And this is when it comes with a low work function materials, where when the Fermi levels aligns, because the work function is lower here, so the band bends down and the electrons here can move easily to the low work function metal or low function material, and then the holes, it will be blocked here because of this band structure. Okay. So this is how the carrier selectivity, and only the electrons will be moving in one direction and holes in the other direction. Okay, so and when you take these materials, this is what we call the high work function and the low work function materials for a hole selective layer and for electron selective layer, and what are the materials that you can use for a carrier selectivity? If you look into the crystalline silicon, this is actually what we call as an electron affinity level, that is a conduction band level with regard to the vacuum level, and this is the valence band level. So you could see this material like titanium dioxide is having a conduction band or electron affinity level is almost balancing with regard to the crystalline silicon. There is only, that is actually crystalline silicon is having a electron affinity of 4.05 and 3.95 and 4.05, and titanium dioxide is having an activation energy of 3.95. So there is only a 0.1 difference in the electron affinity level, and that is why this titanium dioxide can form a very good electron selectivity, because this will be almost same level as the conduction band of crystalline silicon. It can act like a very good electron transporting layer, but it can block the holes coming into this direction. Similarly, zinc oxide can also act like an electron transport layer, and which can block also the holes. And there's other materials. If you look into MOO3, for example, there is a huge difference, because this is having a high work function material. So its Fermi level, and MO3 is an N-type material, which Fermi level will be more closer to here. And when these two crystalline silicon comes in contact with an MOO3, and MO3 the bands will move up. So the crystalline silicon bands will move up like in this direction. So these are the class of material, that is MO3, vanadium pentoxide, tungsten oxides. These are the materials which can be used as a hole selective layer, and these are the materials which you can use as a electron selective layer. So these are carrier selective contacts, transition metal oxides, that is a normal, this type of materials, that is the materials which are between 3 to the group elements of 3 to 12, and especially this copper oxide, moly oxide, and magnesium, and these are the materials, titanium dioxide, zinc oxide, these are the materials used as electrons, hole or electron selective contacts. And if you look into the conductive polymer type of thing, then we can also even use a PEDOT PSS as a conducting polymer, which gives a very good alignment with the crystalline silicon for extracting the holes. And then there are also alkaline earth compounds like magnesium fluoride or titanium magnesium oxide. This type of materials can be used as an electron selective contacts. And these are, okay, this actually I meant for another section. These are the third group to 12 group. These are the materials which are normally transmission metal oxides, but now we are sticking our discussion to only few materials in this lecture. And so first of all, I'm saying about, going to discuss about some hole selective layers in the solar cells. So the first one is what we have recently developed that we called as a boron doped copper oxide as a p-type hole selective layer. So normally, a copper oxide, we have made it into a p-type material and a Cu2O, and it's a p-type in nature. And when it comes with the crystalline silicon, this will form a band bending up, like what I was saying, and then it will be forming, blocking all the holes, or blocking all the electrons, and it will be allow only the holes to move in this direction. And this is what we have done. That is, we chose this boron doped copper oxide as a hole transporting layer, and this is having a band gap of something around 2 electron volts. So it allows all the other energy radiation to pass into the solar cell. And copper oxide and nickel oxide are basically two materials which are showing a p-type conductivity, and which electron affinity values can match with silicon to form a hole selective nature. And they have a high delta EC, and they have a very low delta EV values. That is a band offsets for electrons and hole materials. And so this is how we did the fabrication of the solar cell. So how we prepared this material. The copper oxide was formed by using a sputtering method, and for that we have used also a boron doping was performed, and this is used as with a co-sputtering method with the copper and boron targets in presence of oxygen and argon, and argon was used as the sputtering gas, and oxygen to have a reactive gas for sputtering. So a co-sputtering method was used, and so this is the XRD spectrum, XRD diagram of copper oxide and copper boron oxide. You could see here when you are doping, you cannot, this is copper oxide and this is copper boron oxide, only the same peaks. There is no additional peaks of boron appears. So this is lattice remains the same. So it's only a small doping of boron happens. And so crystallinity actually decreases a little bit because of the intensity change when you are doping with the boron. And if you compare, the different, I'm just skipping this slide. This is actually how you identify the band gap of the material and work function of the material from the XPS analysis we have found out. And it is something around 4.4 electron volt for copper oxide, and with the boron doping, it is 4.64. And once we have this band gap and the work function, and then you could find from XPS, that's ultraviolet photoelectron spectroscopy, you could also calculate what will be the delta EV value or delta band offsets. So from that, you could create a band structure. Okay, forget about it. So we created the band structure of a copper boron oxide with the silicon, and this is the silicon you can have, and this is a copper boron oxide. And when it comes in contact with silicon, it shows a very small band offset of 0.08, which is very negligible for the p-type delta EV, which allows the holes to move in this direction, and it can move on to the contact of copper boron oxide. Whereas it forms a very high band offset, that's that is a delta EC of 1.35 electron volt, which blocks all the electrons coming into this direction. So this selectively allows only the holes to move in one direction and blocks all the electrons coming in this direction. And so copper boron oxide can effectively use as a contact, as a HSL contact for a crystalline silicon solar cell. And this is what we optimized with the different solar cells that we fabricated. And these are the different IV curves, IV characterization curves we did with the optimization of copper boron oxide for different thicknesses. And the best thickness that we found was, the red one, that is a 10 nanometer. And we changed the sputtering power of boron, which changes the doping level. And the optimum power that we have found for the boron, that is, if we increase the power, then the doping concentration will increase. So the optimum power that helps us to get the better IV characteristics is the 5 watt. Okay, so in combination, this 10 nanometer thickness and the 5 watt was used for the other solar cell fabrication. And you could see here, if you are using a 5 watt, all the solar cell parameters, that short circuit current, fill factor, and open circuit voltage are all high. And this is what we chose, 5 watt and 10 nanometer thickness. And we fabricated a device, a full heterojunction solar cell using a copper oxide and silicon, which showed an efficiency of initially only 0.64%. Then we tried to dope it because it's having a high series resistance of this one. You could see the green one. So we doped it with the boron, which improved the efficiency. You could see this curve to the yellow one. And then further, to improve that, we put a silicon oxide in between by a natural, like if you expose the silicon over dipping it in a hot nitric acid, it forms a silicon oxide on the surface. And then we did this copper boron oxide deposition over the top. And the silicon oxide helps in giving a better passivation. And that passivation helps to improve the open circuit voltage from 290 to 370. So this was our first report on this copper boron oxide used as a carrier selective layer. Or this is even the first material, a P-type material of copper boron oxide, and its application as a carrier selective solar for a carrier selective solar cell with the silicon. Okay, so now we move on to another material that we called as MOO3, that is a metal oxide. It's a transition metal oxide, and that also can be used as a very good hot selective layer with the crystalline silicon. Here, slightly different than the earlier one. In the earlier one, copper boron oxide was itself as a P-type material, and which gives a very good band alignment with the silicon. But when it comes to MOO3 is actually an N-type material, but how it behaves as a hot selective layer? Because MOO3 is having a very high work function, and when it comes in contact with the silicon, the band bends in the upward direction. So it blocks all the electrons here, and it allows the holes to move in this direction. And so this is what you could see here. MOO3 is like this, and when it comes in contact with the silicon, the bends in the upward direction, and there will be a lot of trap levels in between this MOO3 and silicon, which helps all the holes to accumulate here, and then it will, it will pass through this defect level states and get a thermionic emission to the or tunnel to the other metallic contact here. And we tried to fabricate a junction like a diode, a dark diode like this, that is using a crystalline silicon, and put N-type crystalline silicon and put MOO3 over the top and put some metal contact of palladium and silver. And if you are giving a biasing to this diode, then you could see it works exactly like a diode. See that it's like a diode characteristics. You have a low minority carrier, like a reverse saturation current, and this is the diode current, which increases exponentially. And when we check, and if you take a MOS capacitor, you can make this MOS capacitor using this one, and then you could measure what will be the built-in potential that is formed with this junction of MOO3 with the crystalline silicon. And it was found to be a 0.69, that is 0.7 electron volt, 0.7 volt, a built-in potential that is formed with MOO3. And it is almost the same like what you get with a normal crystalline silicon and N-type thermally diffused layer. It's very comparable. And if you look into the lifetimes, that before fabricating the solar cell, we took the minority carrier lifetime in the device by the MOO3 deposition. It was around near to 500 microsecond. And the implied VOC that we could get, that is a if you are making a solar cell without any metallic contacts, this may be the predictable implied VOC, that is near to 600 millivolt that you could get. And for a normal crystalline silicon solar cells, you could say the normal open circuit voltages are 630 millivolt, apart from heterojunction. Heterojunction solar cells have open circuit voltages in the range 720 millivolt to 750 millivolt. And so this was very impressive, because we just need to thermally evaporate an MO3, taking MO3 and then just evaporate it, and then you are getting a very good passivation effect, and that is why it is showing a high lifetime here, nearly 500 microseconds, and a possibility for a higher open circuit voltage for the solar cell. And this is the first solar cell we made with a MO3 on one side, and over the top we put an ITO as a contact layer, and then a silver grids over the top. And on the back side, we put an N+ layer by thermal diffusion. And this forms like a single heterojunction solar cell now. This is a dopant-free metal oxide, moly oxide on one side. And the efficiency we got was something around 13% efficiency. And this is a very good IV curve with the 1 centimeter square area solar cells. And this is an EQE external quantum efficiency curve. And you could see, this even in the shorter wavelength region, it is very wide transparency, and it is much better than normal crystalline silicon solar cells with the thermally diffused N layers on this side. But there is a lot of improvement is needed, because the passivation quality may not be that efficient like that of N-type crystalline silicon and normal homojunction solar cells. But it's a very low cost method, which we could get into an efficiency of 13% just by thermal evaporation of MO3. Now coming to an electron selective contact. So we were discussing about the hole selective contacts till now. So now let us move to an electron selective contacts. So one of the material that we have explored is a titanium dioxide. And like what I've told you, titanium dioxide, it forms a very good band alignment with the crystalline silicon. So it can allow the electrons to move, and it can block the holes to move in this direction. Okay, and so this we have tried by depositing a titanium dioxide of 3 to 4 nanometer by atomic layer deposition. And then we tried to fabricate a device just like a diode, and we tried and biased this diode and took the dark characteristics of the diode. So we could see that the dark diode characteristics exactly comes in as a diode characteristics, where an exponential increase in the diode current and with the diode reverse saturation current here. And so this works, titanium dioxide works an efficient, we can say an efficient, it works like a p-n junction, where it works like a p-type crystalline silicon and n-type thermally diffused layer. So titanium dioxide crystalline silicon works as an electron transport layer and works just like a p-n junction. And so, in order to improve, so what we tried is we tried to deposit the titanium dioxide at different temperatures by changing the ALD atomic layer deposition parameters. And we found that, at the lower the temperature of the plasma, this is actually done using a thermal ALD. And by changing the different temperatures, we found it is better to have the built-in potential, that is the bending that happens when P and N junction forms. That bending, it was high, that the VBA value was high for a low temperature thing. So that was something around 0.55 volt that we are getting for the built-in potential with the titanium dioxide. So this was the test structure, and this was the built-in potential. And you could see this is the conduction band here, right? So as low temperature, we have what we expect is we could see a low oxygen vacancies that is formed. When oxygen vacancy is formed, this material will become more and more N-type. So that is the Fermi level will go up, so that this difference VBA will start increasing. So that is that is what we are expecting. If we increase oxygen vacancies, we could increase the built-in potential. So then we introduced a novel method to increase further the oxygen vacancies. We subjected this film, the atomic layer deposited titanium dioxide, to a plasma, that is a hydrogen plasma treatment, as a low temperature treatment, that's a room temperature plasma treatment method. And this is normally the VBA will be, and when you are exposing this material to a plasma treatment, there will be hydrogen, a reduction reaction will take place, and which increases a lot of oxygen vacancies in the sample, which results in pushing the band down or the Fermi levels to the up, so that you could see the conduction band, the band gap of this material slightly increases because not band gap, sorry, the Fermi level goes up because of the conductivity increase, because due to the vacancy increase of oxygen. And that in turn helps to increase the built-in potential. So you could see by a hydrogen plasma treatment of this layer, you could increase the built-in potential, and that you could show it in the device. That is, this was a deposited device with a VPA 0.52, a marginal increase of up to 0.62. We could get it by a hydrogen plasma treatment. And so this is which we could prove it by an XPS studies. That is, this is a deposited film, and when we take this oxygen OS, the oxygen 1s peaks, and then analyzing by the curve here, that is, we could deconvoluting the peak of 1s curves, you could identify the oxygen vacancies at 532 is increasing. So this is how the hydrogen plasma treated, the oxygen vacancy percentage is increasing from 28.5 to 40.4% for plasma treatment. So this structure, when we try the normal titanium dioxide, normally what we are getting is, as deposited was getting, we are having a lifetime of only 5.25 microseconds, which increased when you did a thermal annealing in foaming gas at 350 degrees centigrade. It increased to 105 microseconds. That is a minority carrier lifetime. But when you plasma treated it at this sample, it moved on to 320 microseconds, and which is a marginal improvement in the minority carrier lifetime, because it passivates, hydrogen plasma passivates the interfaces to get a very high lifetime for the minority carrier. And this, you could see the dark diode. This is the annealed sample, and this is the plasma treated sample. You could see a straight line portion is increasing. That means the ideality factor of the diode is increasing, is reducing. Sorry. And so this is a solar cell we fabricated. With the one side, we put a Mo3 of 7 nanometer. Other side, you put, that's a whole selective layer. And other side, we put an ETL, that is a titanium dioxide. So when this solar cell is fabricated, we could reach into a solar cell efficiency of something around 9.52% efficiency. That is a heterojunction solar cells with both sides without any dopants. We are just using a evaporated moly oxide and ALD deposited titanium dioxide on the other side, and a metal on the one side, the back side, and ITO on the top as an anti-reflection coating and as a front contact, and then with a metal grate. And then we anneal the sample. Then we increase the efficiency up to more than 10%. This was the results with a normal, low-cost, dopant-free crystalline silicon solar cells by carrier selective method. And then we further, rather than titanium dioxide, why not we can have a fully evaporated thing? So we tried to put a magnesium fluoride as on the backside. What happens with the magnesium fluoride? When magnesium fluoride comes on the backside of an N-type silicon, that is, when there is only aluminum, it forms a band bending upwards with an N-type silicon. When and magnesium fluoride is introduced between aluminum and N-type silicon, the band bends in the downward direction due to the dipoles which are existing or fixed charges that are existing in this magnesium fluoride thin film. And normally the thickness of the magnesium fluoride, since it's a dielectric layer, it is to be very specifically controlled between 1 to 1.5 nanometer. But when a metal layer, aluminum and magnesium fluoride comes in contact with an N-type silicon, bends downwards, giving an opportunity for an electron selectivity, and which gives a band offset for the holes to move in this direction. And this has been successfully done to fabricate a device. You could see here, there is on one side, you put a Mo3 on the front side, and a magnesium fluoride is put on the back side of a crystalline silicon solar cell. And this is both Mo3 and magnesium fluoride were thermally evaporated, and ITO was done by sputtering, and the efficiency was something around 9.4%. So we further tried to find another new materials, and the other one was magnesium oxide. We just put a magnesium oxide on the one side. This is also the similar way. When magnesium oxide comes in with an aluminum, bends downwards at that point, and it forms a efficiency. And this is the dark diode characteristics you are showing with a N-type silicon. Let's say, let's go into the efficiency. So the initial efficiency was something around 4% with this type of structure. But this, this was just to showcase that even with an evaporated magnesium oxide, you can have a very good electron transport layer. Now I'm going to conclude this with a very small introduction about a novel challenging methods that are or futuristic solar cells which can have in our near future, I believe, and that is based on 2D and TDMC material. And there are different types of 2D materials. For example, there are graphene, and then there are boron nitride. Boron nitride is a very large band gap material, and graphene, as you know, is like a zero band gap material. And if you look into the different materials and the band gap energy, and something near to 1.5 gives the better materials, and you could see this MOSC2 or MOS2, this type of materials works better. That we called a molybdenum or a tungsten-based chalcogenides. That's a transition TMDC, transition metal dichalcogenides. They works with a band gap energy between 1 to 2 electron volt, and they are very ideal to be used for the solar cell applications. And so this is why it's an atomically thin. And so there's a challenging opportunities for a next generation photovoltaic devices where we can go for a very flexible devices. And there are this type of material, MOS2, MOSC2, tungsten sulfide, moly-telluride. These are materials which you can use as a 2D materials, as an electron selective contacts or a salt selective contacts for a crystalline silicon. And this is a normal structure of a 2D material from top, and this will be like a metal will be sandwiched between two dichalcogenides, and this is a structure of a 2D chalcogenide, transition metal dichalcogenides. And if you look into the band gaps, for example, these are different materials used in the photovoltaic industry. And if you look into the TDMC, that is a transition metal dichalcogenide, they have a band gap energy which is very ideal. This is 1.34 is the ideal band gap for making a solar cell. And its value is mainly, that is, the interesting part is if you're having a bulk, it is having a high band gap of 1.8. And when the bulk material is changing into a few layers, that is 3 layer, 2 layer, a single layer, mono layer. When it comes to a mono layer, it forms a very ideal band gap. Or we can say in the mono layer materials are having a direct band gap, and bulk materials of TDMC are having an indirect band gap. And a few layers of 2DMC materials, the TDMC material will have an ideal band gap near to 1.34, which gives a very huge potential for a 2D materials to be used as a solar cell material. And if you look into the absorption coefficient here, you could see it's a huge absorption coefficient. Normally, for example, silicon is a very low absorption material. Gallium arsenide is nearly 10 to the power of 5. And you could see this absorption coefficient is very high, of the order of more than 10 to the power of 5 for 2D materials. And if you compare the different absorption curves, this is a gallium arsenide curve. It's a very sharp absorption. And if you look into the tungsten selenide, it is weakly absorbing. But if you look into this molybdenum sulfide or a tungsten sulfide, you could see a very sharp absorption peaks, just like the gallium arsenide, having a direct band gap. And this can be actually gives a very huge potential for applying as a solar cell, and also for applying it in photo detectors because of this very good sharp absorption edges. And if you look into the different cells, so these are the efficiency. So theoretically, if you are having a band gap near this value, then these are the theoretical maximum efficiency of the solar cell can have. So there's a potential for a monolayer TMDCs to have an efficiency near to 25%. And so this, I'm showing something called using a graphene as a carrier selectivity layer. So when graphene is not having any band gap, but it is having a work function, and when it comes in contact with an N-type silicon, the bands bends in this direction, and this is actually forming a Schottky junction with the crystalline silicon. And when it forms a Schottky junction, when it illuminates, there's a barrier for the electrons, and only the holes will be transported into the graphene. So graphene works a very good hole transporting layer with the N-type silicon. And you could see an efficiency that this is a solar cell that is fabricated with a graphene as a hole selective layer. And the efficiency is not that high, but this is to prove the potential where applications of graphene to be used. Another one is, I'm just showing a silicon MOS2 carrier selectivity. So if you are putting an MOS2 over the silicon, and then, it forms the bends in this direction. And this molysulfide forms a Schottky junction with the silicon, and it forms, the band bends down, and the electrons can move in this direction. So, and also, the holes can move in this direction. A MOS2 silicon, forms a very good band bending, and this holes from here cannot move in this direction because of the band offset. So electron moves in this direction, holes moves in this direction. And an efficiency of 5.3 has been demonstrated for this using 2D materials as a carrier selective material in the solar cells. So this is a futuristic applications of solar cells. With that, I am concluding, and I'm acknowledgements to my PhD students who completed recently, Dr. Kurias Marcos in CUSAT and Sosti Bhatia in IIT Bombay. And also I'm thankful to my collaborators, Professor M.K. Jairaj, current Vice Chancellor, University of Calicut, and who was the head of the department and professor at the Department of Physics in CUSAT. And then Professor Pradeep Nair, who is a professor in electrical engineering in IIT Bombay. And also thankful to National Center for Photovoltaics and Research Education in IIT Bombay, and MNRE, Ministry of New and Renewable Energy, and the DST SERP for the funding for the project through MNRE and DST SERP. And so thank you. So, and I'll be happy, if there are any questions from your side, we could.
Thank you, Professor Aldrin, Anthony. I think we all have got very good talk on the solar cells and also two-dimensional or thin film solar cells. And he also gave an introduction about polymer solar cells also in his talk. And it is very interesting. But I have one question to you. Now also, mainly people are using silicon solar cells. I think there are several reasons. But even though there are so many materials we have, our research people made, but now also the major part of the silicon solar cell companies are based on silicon. Why? What is the reason? And why we are not going for thin film solar cell for commercial applications? Can you give?
The major, or I can say there are only one major reason. Major reason is the cost direction. Crystalline silicon, even though we say that it's a high temperature process and all these things, but when it comes to a large processing, and crystalline silicon shows the highest efficiency. And also in terms of with regard to the reliability. If you want to buy a thin film solar module, it is still expensive to buy a crystalline a thin film solar module. And major thin film module technologies that were amorphous silicon, which couldn't go beyond 13% efficiency. And the other one was CAGS. In module level, it was only 18%. And cadmium telluride is the only one which showed the efficiency up to 16% or 17% by, and still it is in the market by First Solar. But I don't see that thin films will come up. I feel like crystalline silicon will dominate the market because of low cost in production and large volume throughput that it is giving. And but the thin films will have like a perovskites that are coming up, which is having a higher efficiency when it is in combination with the silicon, giving a very high efficiency up to 30%, is still having a big chance for as a major play in future. Once it shows that the perovskite solar cells can have a higher lifetime. And there are different ways of approaching it, like a 4-terminal device or a 2-terminal device, because currently the time scale or the efficiency over a period is a concern for perovskite solar cells, the stability issues. So this is one of the reasons, because the cost is very difficult to manage compared to crystalline silicon. And that is actually happened because of the Chinese innovation. We should accept it, because Chinese played the major role in decreasing all this efficiency of, not efficiency, the costing of solar cells. And most of these materials which you needed for fabricating the full module is coming from China only, and not even Europe can compete in that. So the technology was made in Europe or in Australia. Even for aluminum frame, we are making aluminum frame, but we have to depend on.
Okay, thank you. Any other questions or queries from audience, please? Because we are running out of time
Yeah.
already.
Yes.
Hello.
Please.
Yes, sir.
Good morning, Aldi. Great. It was a great presentation that we really enjoyed. It's just give a very comprehensive overview of the silicon sources and state of that at the moment. The talk was mostly concentrated around the electrons transport layer regarding your. So how the electrons transport layer will have any effect on the light transmission into the junction on field? Will that affect in any way?
For example, the electron transporting or hole transporting layer which are being used are transition metal oxides, which are in principle, it's almost like a dielectric materials. And their transparency is really high, nearly 95% compared to doped layers. So when it is a doped layer, obviously there will be a lot of absorption by the free carriers happens. So that is the beauty of using a transition metal oxides, which helps, there is no point of this type of free carrier absorption with this. And it's a very thin layer, so there is no losses of absorption by these layers.
Okay. Well, what are the typical thicknesses of these layers?
The layers thickness is normally for a moly oxide, if you are using, it's a maximum that we can use is like 15 to 20 nanometers. And if it's a titanium dioxide, it is restricted in 4 nanometer. And normally you need to have a good conformal coating. So normally ALD gives the best coating for this 4 nanometer. And now the ALD has become a very industrial tool in China, especially for PERC solar cells. So it's not like what we are feeling like ALD takes a long time. Spatial ALD and everything are already in the industry.
So you got these huge deposition systems and things like that?
Yeah. Very fast also, fast ALDs.
Okay.
And actually during the lockdown, after the lockdown, China made a lot of innovation in these things.
Yeah, they got time to change things.
Yeah.
Thank you. Thank you. Cheers.
Thank you.
Any question?
Yes, I have one question. Hello.
Yeah, please.
Please. Any?
Yeah. So my name is Kenneth Lobo. I'm from Center for Nano and Soft Matter Sciences, Bangalore. A very nice talk, sir, in fact. And my question is that there is a lot of research right now looking at self-powered photodetectors. So where do we draw the line between a self-powered photodetector and a solar cell?
So these are all two different applications, right? So one is your power generation. You're looking at a huge power generation, right?
Yes, but where do we draw the line between a self-powered photodetector and a poor solar cell, so to say?
So, I mean, you want to know about what do you mean by exactly draw the line between detector and a generator? Because a detector is actually working only with a direct bandgap semiconductor, and it's slightly different, the working principle, right?
Yes, but even with heterojunctions, this has been achieved.
This is basically it's a heterojunction of epitaxial heterojunctions that is basically used for detectors, which showing a better efficiency detectors. But when it comes to this type of silicon, is a very bad detector, right? For example, if you compare it with other materials.
Right.
So, I'm not sure what exactly you are trying to convey it by the line between these two, because if in terms of material property, this depends on all the interface defects that comes into play for the direct band-to-band transitions, right? And that is more critical in also the detectors.
Yes.
And here you need to find how you could easily extract the carriers by slightly different than recombining band to band. You are selectively removing the carriers from the junction.
Okay.
Okay. If no more questions, okay, we can, I think we can move to, hello? Any other question? Any other question? If no more questions, we can thank the speaker, Dr. Aldrin Anthony, for his nice presentation. And thank you, sir.
Thank you, Dr.
Now I
Pradyuman.
can
Thank you, Dr.
hand over
Chen.
my microphone to the organizers and who is next speaker, and please give an introduction. Okay, thank you, sir.
Thank you.
Thank you.
Is being recorded.
Hello. Hello, now I think now we can move to the next speaker. Can you hear me? Audible? Prashant?
Yes, sir. Yes, sir. You are audible, sir.
Okay.
Pradyuman, sir.
Okay.
Can we go to the next speaker, please?
Can you hear me?
Yeah, yes, we can.
Am I audible? Okay.
Yes.
Yeah, okay. Now the next talk by Professor Prashant we have here. He is a very good friend of mine. He is from Pondicherry University. And now on behalf of all of the organizers and of ICMPMA, I welcome Professor Prashant. And let me to give an introduction about his biography. Dr. Prashant Ravindran received PhD from Eindhoven University of Technology in Netherlands for the thesis entitled Photonic Switching in 3-5 nanostructures. He pursued his postdoctoral research at Peter Debye Institute at Utrecht University. His invention on resonance enhancement of second harmonic generation and polariton confinement in nano cavity leads to the development of polaritons lasers. His current research interest is the development of one-dimensional and zero-dimensional nanosystems for solar energy conversion. He published research articles in leading international journals such as Applied Physics Letters, Physical Review Letters, Advanced Functional Materials, Electrochemica Acta, Journal of Electrochemical Society, Journal of Quantum Electronics, Journal of Power Sources, Renewable and Sustainable Energy Review, Journal of Colloids and Interface Science, etc. And also presented papers in many leading conferences in Netherlands, Germany, France, Belgium, United States, Japan, Singapore. He also serves as a reviewer of many leading scientific journals. His research interest is in developing metal oxide heterostructures for solar energy harvesting. In the last 3 years, he developed super hydrophilic nanotube surfaces that enhance the heat flux with less superheat, which has potential application in solar direct stream generators and cooling applications in integrated electronic devices. Recently, he also developed PEC with titanium dioxide, cadmium sulfide, nickel heterostructures, solar to hydrogen conversion. He also received many awards and honors: Best Teacher Award 2012, Pondicherry University, Postdoctoral Research Fellowship, Peter Debye, Netherlands University Federation for International Collaboration Fellowship for PhD, etc. Now I invite Professor Prashant for his talk, Titanium Nanotubes, a sustainable green energy material.
Thank you, Professor Pradyumnan, for your kind introduction. And I also would like to thank Professor Jim Jones and Professor Sunil Thomas for providing me an opportunity to deliver this lecture, some of our research activities that will help us also to make a better understanding of our mistakes. So this is our school, Green Energy Center at Pondicherry University. We are offering PhD programs and MTech in Green Energy Technology. My group is extensively working on nanomaterials for solar energy harvesting and storage. Can you see my slides? Hello, can you see my slides?
We cannot see.
No, sir. No, sir. We can't see.
Yeah, can make full screen.
Okay.
Yeah. It's okay now.
So,
yeah, thank you.
Fine. Okay. So these are the materials so far we worked out. Some of these are using quantum effect. That means you can confine the electron in a very small special region that can help you to manipulate the optical and electrical properties of the materials. And we developed two-dimensional nanostructures. There you can confine the electron in one direction. And our interest is mainly harvesting light, or what will happen when light is interacting with the nanomaterials. In that study, we developed zero-dimensional structures, one-dimensional structures, and also nanostructures. You cannot say it is a quantized structure, that is nanotubes. Nanotubes, today I'm going to expand about TiO2 nanotubes. That is not a quantized structure, because TiO2, as you know, it has a very high effective mass. So even with a very small size, it will still show a parabolic band density of state. So it is still a bright material, but you can do many interesting energy harvesting effect with this material system because of its high surface area. Primarily, it's a high surface area. It is easy for you to make this material, but the challenge is making other required properties for optoelectronic application, mainly the conductivity of the material. So we are trying to improve the physical properties of the material by applying some very trivial, simple physics that is easy for all of you to understand. Titanium dioxide is existing with three main allotropes, that is anatile, rutile, and project structure. It is chemically inert and it has high surface area, excellent ionic transport, and high diluting capability. With that property, people start working with solar energy harvesting, because it's first in the energy devices, means solar energy devices. The dye sensitivity solar cell may be the first one developed with this material, and it has good electron affinity. Its no toxicity is another attractive property for making device structures. And the nanotube fabrication is very simple. Electrochemical technique you can use to develop this material, where you're using a titanium foil as a anode and a platinum electrode as a cathode, and applying some voltage. That's it. You have to play with the electrochemical conditions to tune the structure of your tube. That means you can play with your voltage. That's the first one you are applying. So the idea is, since the increased surface area, that means in a given geometrical area, you have to make more surface area, so that your in the case of a solar cell, for example, you can include more light harvesters in a given geometrical area if you increase the surface area. So the simple trivial technique is to make a porous structure. So if it is a tubular structure, you can make a very good surface area. That's a very simple thing to understand. So when you're playing with the voltage, you can apply voltage of electrochemical fabrication. You can change the diameter, primarily the diameter of the tube, within some error. It is not a very accurate control you will get, but you can play with other electrochemical conditions also, so that you can understand what will happen with your structures. So in the beginning of our research with TiO2 nanotubes, we played with many factors that influencing the structure of TiO2 nanotubes. So what is the impact of electrolyte into the structural properties of or morphology of the tube, and the growth rate of the tube, because different electrolyte compositions can give different growth rate of nanotubes. So many things you can play with in the fabrication of nanotubes, and the extra species coming to the electrolyte is basically an etching and regrowth process. So you are using the fluorine to etch the titanium surface in a controlled way. So you will get a porous structure that the removed TiO2 again redeposited over the nucleated regions, and it is regrown. That is a simple way of viewing the growth of the nanotube structures. And then you can study the thermal properties of this material, because many applications, some of our applications at least, we have to understand how the structure is changing with high temperature, and otherwise also in a lower temperature region, its crystallinity will change. So certain crystallinities are favorable for our device applications. For example, in 250 degrees Celsius, you can get an anatase structure that is very useful for dye-sensitized solar cell and heterostructure formations. And when we are dealing with the thermal applications of the material, we have to go to a very high temperature. So whether this structure can stand high temperature, that's very important to know. So these studies shows that it can go up to 600 degrees Celsius. After that, it shown a collapsed structure. So you can see the top view and lateral view in this some images. And then we are doing a lot of characterization techniques to really engineer this material, but I'm showing very few things that is easy for you to follow me for this particular lecture. So when you're changing, the first thing you're looking is an XRD pattern and comparing it with the standard pattern, and how with the thermal annealing, how that structure is, how the crystallinity of the structure is changing. So that's very important property to understand the device behavior of the material. So now in the application level, this is about the fabrication. It's a very simple way I explained the fabrication of the nanotubes material. And then coming to the solar cell applications, the first thumb rule, that is means you have to include more light absorptions in the structure. Very simple logic we are applying. That means either you can include more dye into the tubular structure, so the dye will absorb light, and then from the LUMO level of the dye, the electron will transfer to the TiO2. TiO2 is naturally an N-type material that will make the electron transfer. So as I told you, the density of state of TiO2, even if it is in 15 nanometer bulk thickness, it is shown, it is still only a bulk material. The advantage of using tube, as I told you, is the high surface area we are getting in that. But when you are loading to more dye, naturally more light will get absorbed by the dye. So naturally you can expect more electron hole pairs. But that is not the only thing making a high efficient solar cell. There are many other factors influencing. I'm not going into all the details of this mechanism of improving the efficiency of the solar cell, but in this talk I'm restricting myself to the possibilities in front of you can play with the titanium dioxide nanotubes. So other ways you can include some quantum dot structures. In quantum dot, that is also a good light absorber. Compared to a dye, quantum dots are more stable, and it has a discrete energy state rather than a molecular energy states, density of states as described in the slide. Then that has only spin up and spin down states. So the titanium nanotube as a bulk state means more states are available in titanium dioxide. So the injection efficiency normally will go up in a quantum dot loaded tubular structures. But when we are playing really with a device structure, it is still showing a lower efficiency compared to a dye-loaded structure, because many other factors are influenced. Means the quantum dot is not really injecting electrons into the TiO2 nanotubes. If you are modifying its surface with in this case we used a Gaussian type of quantum dot structure, that is CDS quantum dot structure, where you have a type 2 potential well structure is coming. In type 2 structure, the electron confinement and the hole confinement are in different layers of the quantum dot. Means electrons are in the core and holes are in the shell structure, more or less like that. That way you can make type 2 quantum dot. So that will make an easy separation of electrons and hole pairs. But still, when we are making a surface modification with ZNS, then it will make a better current. That means the interaction with the quantum dot and the titanium dioxide, that means the linkage of quantum dot, that need to be improved for making a real current injection into the TiO2 nanotube structures. Another possibility with TiO2 is TiO2 nanotubes is making a energy storage device. TiO2 is extensively used for energy storing applications. Many with other materials, either TiO2 as it is or with a composite of TiO2 is using for the energy storage, and it is showing as a good competitive material, but it's still the energy storage capacity is in the lower side of the record commercialized materials. So the simple idea again in this case is energy density is assumed it is a half CV square. So either you improve C or you improve B. So if you're looking for improving the C value, capacitance specific surface area, that is the primary factor you can improve, and the pore size, electrical conductivity, and additional redox capacitance can be improved. So how to do that? Making it into a tubular structure, you can improve the electric double layer formation inside the structure. So electric double layer capacitor is a good possibility with this nanotubular structure. That will the porous nature of the material. When you are making small and small pores inside the surface, more surface area can be generated. That will give a high electric double layer formation inside the porous structure of the capacitor. So when you are doing this characterization technique, the typical characterization is as compared to a battery or a supercapacitor, it will show a square type of current potential characteristics, the CV characteristic you can say. So in that case, what we can see with a single titanium dioxide tube with some electrolyte like HCl or sodium chloride like electrolyte, you can use different electrolyte systems. We worked out this. You can see there is a reasonable capacitance, but it is not commercially competitive value, and it's showing a good stability of electrical storage. So if you increase the carrier density, that's next simple logic. You can increase the conductivity of the material or increase the carrier density of the material. Carrier density of the material is increased by annealing it in different environments. So you get different carrier densities inside the system. So you can see in such cases, we are able to get a better square type CV diagram and showing a good aerial capacitance. This is a few years back work only. And after that, we didn't do too much in this direction, but now is other researchers show a better value. That time it was a good value, but now we have an improved value because we focused on different aspects of improving the material properties during this time. The logic is improving the conductivity of the material. What are the different possibilities of improving the conductivity of the material for getting a high storage capacitance, or also other photovoltaic devices and hydrogen production devices also. For getting a better performance with light harvesting, you need a better conductivity for the material. So the possibility is increasing the surface area or increasing the electric current. So through ionization optimization, we can play with the porosity and surface area of the material, but the electrical conductivity part still need to be improved. So the possibilities are doping with different materials with TiO2 and the co-doping techniques. So doping is happening in this way, and co-doping also can be applied, means two materials can incorporate into the crystal structure of the material. So different possibilities are existing. Lot of possibilities are existing with doping of the TiO2 material, and co-dopant are also identified. Lot of possibilities are there. We have to make the clever choice by studying the effect in the photon to incident photon to current conversion efficiency of the material after doping. So that need an extensive research in this area, and copper doped structures are showing a better effect in this way. So that is making a very high photon to current conversion efficiency, incident photon to current conversion efficiency. That means what is the effect of copper in this structure is it's making a band gap reduction by making interstitial energy band structures and improved optical responses, suppressed charge carrier recombination and increased short circuit current, and high thermal conductivity, high electrical conductivity, and cost effectiveness and non-toxic nature. So if you're doping the material, with the crystallinity of the crystalline size of the that will also change. With that, the efficiency there is an optimum crystal size it shows for making a high efficiency value in this material. And again, the copper doping also can be done with a simple electrochemical method. That is an advantage. That makes the system fabrication very cost effective and simple. And if you want to scale up, you can go with a bigger chemical bath system. So that is a major advantage of working with an electrochemical system. So the fabrication process can be very simple. Any laboratory, you can make this kind of structures. That is an advantage. And doping process also can be done with a very simple, cost-effective technique. That is the thing. And then we have to do a lot of characterization, but we make. I'm showing some few characterization techniques only today. This is a Ramen mapping that will help you to understand how the doping is happening within the entire structure. So in a region, that picture, the color variation shows the polymorphic or concentration of the material and change of the geometrical conformation of the molecule in question, and the presence of small amount of other impurities in the material. The first picture shows the pure titanium dioxide nanotubes, and the second picture shows the copper doped with a small concentration, and when what will happen when the copper is doping with a high concentration. So that means this deposition technique is very good for introducing copper into the structure. And if you're studying the same picture, that will this kind of modification, that means it's maintaining still the porosity of the structure very well, and it is making a very stable structure. And then we can study the photocurrent behavior of the system. After copper doping, you can see a good improvement in the photocurrent density of the material and also the impedance. If you study the impedance behavior of the system, you can see a considerable reduction. That is the most important part of the study. The impedance of the electrode is considerably reducing by incorporating such doping. So that is one element. And so the next application is the hydrogen production. In hydrogen production, that is simply doing by water splitting, because hydrogen is the cleanest energy possible in the environment. But the current commercial hydrogen production methods that are not completely a green pathways, emission is happening in that. If you use solar energy for producing water splitting, then you could be able to reduce the carbon footprint of the hydrogen reduction considerably. But how to give the required energy, because there is an energetics working in the splitting of water. You need 1.23 eV energy to split the water. So titanium dioxide can provide, because its band structure is appropriate for producing the potential for water splitting. But the problem is titanium dioxide is a wide band gap material, so it cannot absorb enough light to generate the electron. So we need to improve that light absorption property. So some other material can give the light absorption. That means you can make a heterostructure with the titanium dioxide, a suitable heterostructure for making a light harvesting. So one material that will make a light absorption, and it will transfer the electron to the TiO2. So you will get sufficient charge and sufficient potential. That means you could be able to produce a potential for water splitting. So there are many materials that has a band alignment which is matching with the potentials of hydrogen generation. So we can choose the material for making a proper heterostructure formation with the TiO2. Heterostructure formation depends upon band alignment, then the band crystals, what's called the lattice parameters, because if the lattice parameter is too high, then it will feel a strain. So in that case, if the lattice parameter is too different, the percentage of strain will go up. So that is that will make a strained band alignment, band structure at the interface. So that interface will leads to a carrier loss. So by making a heterostructure, you have to be careful with many such engineering parameters for making band structure. Now, in this case, we used a CDS nanoparticle that can be nicely decorated with the TiO2 nanotubes. So CDS can absorb light from the visible region of the light, solar spectrum, where you have maximum photons available. So that photons can be harvested, and then electron hole pairs can be created. That electron can be transferred to the TiO2 nanotubes. So when we are doing with this TiO2 CDS structure, the main problem is its instability. CDS is not very stable with the heterostructure formation. So you have to make a proper stoichiometry by adjusting the deposition of CDS. Means you have to make a correct stoichiometry of CDS, 1:1 proportion, 1:1 proportion. So we played with the time of deposition, and at what time you are getting the right stoichiometry of the CDS. That shows a better performance of the device hydrogen production in the electrochemical cell. So in this CDS, the TEM images shows that this CDS is nicely going and decorating into the nanotube structures. So and when we are decorating the TiO2 nanotubes with CDS nanoparticles, then you can harvest more light into the system, and that will transfer compared to a normal TiO2 alone. That's showing the black curve. And when you are increasing the deposition time, that will increase the size of the CDS nanoparticles. And at certain point, when the stoichiometry is proper, that shows a better current, light absorption in the structure. After that, it will again decrease. And then we are working with the PEC cells, photoelectrochemical cells, that shows the proper stoichiometry. This current generation, photocurrent generation is very good. And when you are playing with the light illumination in an on-off state, it is showing a very good stability of the electrochemical cell. That means the cell is responding very well, very fast, and its stability is also very good. Now, after including the CDS, you can see the impedance of the electrochemical cell is also changing significantly. So that means a good current flow is happening in the device structure, and you could be able to produce good amount of hydrogen with this electrochemical, this electrode. And the next is again how to improve further the light. That's one way. Improve the light harvesting of the electrode. You can make better photo current, or you can make better hydrogen production. So we use a nickel nanoparticles, that's a metallic nanoparticles, that will make a plasmonic effect. Means it can trap more light into the device structure. So nickel will also trap some of the light with the plasmonic effect, and that light can be injected into the CDS system. That will generate a electron hole pair, and that electron hole pair can be injected into the TiO2. That means you are harvesting more light from the solar energy. So in that case, again, you have to optimize the structure. When you are making a proper deposition of the nickel nanoparticle, that can harvest more light through plasmonic effect, and also it is acting as a protective layer for CDS degradation. That is an additional advantage, that you can see how the light harvesting property of the electrode is increasing by including the nickel nanoparticle into the system. So that means you can generate more photocurrent. It is means more light absorption, means more photocurrent can be generated with this electrode system. And then also the stability of the electrode, that is also you can keep better, and the production, hydrogen production rate also can be enhanced with this electrodes. And you can see the impedance is considerably decreased by including the nickel nanoparticle into the electrode system. So a clever design of the heterostructure with TiO2 nanotube, which can harvest more light and transfer the electron into the TiO2, can reduce the impedance and increase the photocurrent, and hence it can produce a good water splitting effect and hydrogen production. Same thing you can play with the solar cell structures also. So many improvements happening in that nanotube so far I discussed as applications in the other devices also, means photovoltaic cells. These heterostructures can be developed for making PV effect also. So copper oxide, you can make a titanium dioxide and copper oxide heterostructure that can be developed to a photovoltaic effect. So many possibilities are existing for that. Now the next thing is the heat transfer. But here what we tried to prove is the tubular nature of the material. that will help to improve the heat transfer efficiency in a pool boiling system. We cannot claim that this titanium dioxide material may be the best one, because again the thermal conductivity is poor in this material. But what the tubular structure can do in a pool boiling system, so that you can improve the heat transfer efficiency in the system. In a direct steam generator, solar direct steam generator, or in a cooling application of a chip, you have to transfer more energy, thermal energy or heat flux with a small superheat. But when the boiling mechanism starts, it is something simple like your coffee pan. You are looking into the boiling mechanism. You can see bubbles are forming, and then bubbles are detaching from the surface, and next layer of water is coming. So that is called the boiling mechanism. And at the CHF, as shown in this graph, at the CHF, the heat transfer become very less efficient, because a layer of vapor will form that will block the transfer of energy, that will reduce the heat transfer efficiency of the system. So what we can do to improve the heat transfer efficiency in such system? For example, in a direct steam generator, you are focusing the light into a tubular kind of furnace, through which you are passing the water and generating the steam. When you really want to make a thermal energy production, you have to produce superheat. But the existence of these two phases, vapor and liquid phase, that will decrease the quality of the steam. So for an efficient transfer, transfer of heat into the system, you should improve the heat transfer mechanism in that. So when you are making a tubular structure on that material, over that material, it will change the wettability of the material. So when the surface is more hydrophilic, both hydrophobic and hydrophilic has surfaces as importance in energy transfer. Means in a self-cleaning surfaces, you are looking for a super hydrophobic material, but here for heat transfer you're looking for a super hydrophilic surface. So that surface, through that surface, the liquid will spread completely. If you're getting a zero contact angle, that means you can make a good water spreading over that surface. And this tubular surface, that will after heating and making the bubble, you can get a another layer. That means the wetting layer that will easily flow. And you can change the bubbling mechanism, the nucleation. All this I will show some videos if time permits, for changed boiling mechanism in the structure. So you can make the tube geometry by changing the tube geometry. You can change the wettability of the surface, because you have two different ways of models of changing the wettability of the surface. One is a Casebox state, in which the wettability, the bubble is sitting over the tubular structure. Means if the surface energy is high, then it will make such hydrophobic surfaces. But in some case, you can make a water inhibition model. Means water is going and filling into the tubular structure. So if you treat chemically with this surface, you can make a high surface, high hydrophobic surfaces, but a normal tubular structure with small pore size, it is making a water inhibition model inside the tubular structure that will allow to spread the water into the surface. So then you can, in such structures, you can study the heat transfer mechanism by making a pool boiling system. So that shows in a tubular structure, in a TNT tubular structure, you can see a more uniform nucleated bubbling compared to a steric acid treated surface where it is making a highly hydrophobic surface. So, and the bubbling mechanism, the bubbling frequency, you can see, I will show you the can you see this video? Hello? Can you see this video?
Yes, sir. Yes, sir.
It is making more uniform nucleation compared to a high surface area or high surface energy material where you have a this means compared to a tubular structure, this structure is making a very slow bubble detachment and refilling of water. So a tubular structure that can make a better heat transfer through the surface. So the efficiency of the heat transfer or the CHF through the heat transfer that can be improved with a tubular structure. Definitely, titanium dioxide is not a good heat conductor. So again, that thermal properties, either you have to improve the thermal conductivity of the material, or you could be able to make a tubular structure with a better heat conducting material. That will make a good surface for heat transfer applications. So this is my story today. Now you can ask questions related to this, or you can even give.
Okay. Thank you, Professor Prashant, for nice presentation and nice talk. And we got very good information about nano titania and their structures. One or two quick questions from audience, please. I think there are no questions in the chat box. I have one question then. Can you hear me, Prashant?
Yeah.
Because what about the, I'm also asking because purification process, energy process, many places this titania is very, very important material. But for commercial application, you know that in paint and other things, there also titania is using.
Yes.
So what are the main technological application now we are using the titania in this? If you are using any hydrogen storage or any other cases, any such things are there already available or not? Have you any idea?
Commercial, you mean commercially?
Yeah, commercial means you know that.
In
hydrogen storage
paints,
now.
it is
Now
extensively
companies are already.
using.
Yeah. Okay,
Yeah.
because technology-wise,
means,
when we are exploiting this particular material, there these commercial things are coming. So that's why I'm asking, because already we know that some vehicles are containing hydrogen storage materials. Already cars are there. So such think such type of research is there or not? And what is your opinion about that?
Titanium, titanium, particularly titanium dioxide, has a lot of applications. Even medical applications it is using energy. But in many cases, the commercialization, if you are asking about the commercialization, only in paint industry, it is, as all of us know, that it's widely using material because it's a white pigment that is very useful for paint industry. Other than that, in this is only a futuristic material. It's still, we cannot say, see, definitely dye-sensitized solar cells are now commercially available, but its competitiveness, if you're considering the competitiveness of dye-sensitized solar cell compared to a silicon solar cell, it is definitely very small percentage only. The point is why we are investing. Definitely, I don't think that we can compete silicon with some other material. Silicon will continue its domination in energy harvesting, solar energy harvesting, particularly photovoltaic applications. It will dominate, but see, silicon is an indirect band gap material, so its light harvesting efficiency is less. So it is more expensive material. But as in the previous talk, Professor Aldrin said, it's by scaling up, the cost can be reduced. But the other alternate materials so far investigated can contribute 10% of the energy only. That's a projection. But by 2050, we need 30 terawatts of energy. That is the projection. So it is 10% of 30 terawatts from all other alternate materials, even if we can make a cost-effective way. That is still challenging, but alternate materials are required. But in the case of hydrogen production, maybe in future, titanium dioxide has a better contribution. But photovoltaic application, if you ask me, it can contribute in a small percentage. That is my expectation. But that even small percentage means it is a big quantum of energy. That's all. But it has a good future in hydrogen production, because other commercial methods even has good carbon footprint. So if we can improve the hydrogen production efficiency about 10% in PEC, based titanium dioxide based PEC, definitely it can make a industrial process.
Okay, thank you, Professor Prashant, for a very nice presentation. Let us thank Professor Prashant Ravindran for his very, very inspiring speech. Thank you once again. Now we are also we running late. Now the today's third presentation after second invited talk by Professor S. Asha Ravind. Asha Ravind is going to talk on applications of density functional theory, DFT, in material science. Dr. Asha Aravind finished her PhD from the Department of Atomic Energy, India in 2013 and further carried out postdoctoral research in IMSC, India, then KAUST, Saudi Arabia. Further, Dr. Asha was a research coordinator at the University of Sharjah and visiting scientist at JNCSR, India. Since 2018, she joined as a researcher at Nanomo University of Oulu. She was a visiting scientist at the group of Professor Michael Nolan of Tyndall National Institute, Ireland, as a part of HPC Europa program during March-April 2022. Dr. Asha also holds a affiliate research scientist position at the College of Science, Northeastern University, Boston. She was over 40 national peer-reviewed publications to her credit and several conference and workshop presentations. Now I invite Dr. Asha for her presentation.
Thank you. Thank you for the nice introduction. Let me share my screen. Are you able to see now?
Yes.
Yes, yeah.
Yeah.
Okay. So my research area is density functional theory, and I mainly use DFT to solve some of the problems in material science research. And the outline of today's talk is I will briefly go through the relevance of density functional theory in science and technology research, and a very brief idea about what is this method and what are the capabilities and limitations. I can show some of the publications in the recent years, and like any other method, theoretical approximative method, there are some limitations as well. So I will briefly go through that as well. So before going to the details, here you can see a slide which I put from a paper published in Nature in 2014, and it shows a paper mountain, as you can see here. So this paper mountain actually depicts top 10 papers published in like top 100 cited papers in last 100 years, and among the 100 publications, top 100 cited papers in the last many years, and these some researchers, they found out that top 10 papers belonging to the density functional theory. They use density functional theory in a very prominent manner. So this is just to give an idea, because these 100 publications actually covered everything, meaning all fields, medicine, industry, chemical engineering, or whatever published so far. From that, they took topmost 100 papers, and in that, the 10 top papers were from DFT. So this shows the importance of having such kind of simulations in today's material science research. Now, what is DFT? DFT is actually density functional theory, as the name suggests. It is basically the electron density which is involved in that density functional, and because electrons are governing everything in the terrestrial world, from materials to like everything, you name it, you have electrons in it. So you have to, every behavior is actually controlled by the electronic phenomena. So we can say that DFT literally underlies every physical phenomena you come across. Now, the first time DFT was formulated in its almost present form by Walter Kohn, and in 1992, actually it's a chemist, even though DFT is mainly used by physicists. The first time DFT was formulated in a software form, successfully executed in a software by a chemist, John Pople, and who shared the Nobel Prize with Walter Kohn. Walter Kohn formulated the theory, and John Pople did the software implementation, which is many of you might be aware of this package, which is Gaussian, widely used by chemists to calculate a lot of properties. So this is to give an idea that it is very widely used these days in the scientific world. Now, what made this rapid growth possible? That is mainly because the increase in supercomputer performance, because as you know, every year the computing capacities are getting exponentially increased. And as you can see here, the data is until 2020, but now if we get another graph which includes last 2 years, it might have jumped much more than this. So this increase in supercomputing powers, computing powers every year is actually contributing the rapid growth of DFT and the the use of DFT. For example, in the 1980s, maybe you need 1 week or 1 month to do a small calculation. Now you can do in minutes or even in seconds in today's fastest supercomputers. So the fastest as you can see here, the adding up of the sum of the top 500 is actually the number one supercomputer is not differing much from this. So that much the computing power has increased, and which is contributing to this rapid increase of use of DFT. Now, from where all this came from? It all came from the Schrodinger equation that you might be aware of. Everybody learning quantum mechanics, it's even in the bachelor's level, you will be learning this. And Erwin Schrodinger in 1925, actually, there is a very nice story behind it. He was actually vacationing in Switzerland during Christmas time, and he was pondering over this theory, and he wrote to his friend in German that I am actually formulating a theory. If I am able to formulate it successfully and solve it successfully, then I can solve almost everything in the material world. So this is the basis of quantum mechanics in 1925, and this is the equation many of you are familiar with. That means the energy of a system is actually the kinetic energy term and the potential energy. Actually, it's the interaction potential. So the electrons are actually represented by wave functions. So the first term is essentially the the kinetic energy term, which includes the wave function. The second term includes the correlation. So if this equation can be solved, we can get everything underlying material phenomena. And but also remember that this is a single electron equation. This is for example, if we consider a material which has only one electron. Now, how to solve this? The writing is very easy. You can think of this kinetic energy and this electron nuclear interaction, and then you get the total energy. But solving this is not easy. For one electron, you can actually think of it equivalent to the second law of motion. And we can solve this by using the separation of variables. And this first term, which is actually you can separate it into time and position dependent part, and you can solve it in that way. And this the solutions come like this. We have this kinetic energy term and the correlation, and then we have a time dependent term. This term is only dependent on the position, and this term is only dependent on the time. So this is how the initial solving of Schrodinger equation and everything proceeded for a single electron system. Now coming to solving that equation, even though it is writing is easy, it's not easy to solve. In fact, it is even difficult than solving this planetary equations. That means solving that equation exactly is in fact difficult than sending people to moon, because there you have to use only classical equations. There you can predict the trajectory and everything classically. But when you come to quantum mechanics, you have electrons, and electrons are represented by the wave function, as we have seen, and the wave function has the probability density, and it's very, very difficult to solve. Now, there were many approximations proceeded after that, and one main important approximation is Born-Oppenheimer approximation, in which Born-Oppenheimer postulated that we have, if you think of only one electron system, for example, we have this nuclei and the electrons. The electrons are continuously in motion, and the nuclei is comparatively slowly moving. So if you can assume like that, the nuclei is moving very slowly compared to the fastest electrons, you can think that at any moment, actually the ground state will be that of the electronic motion. So the electrons are, we can think of in this way, the electrons are actually moving in a field generated by the nuclei. Nuclei are massive and sluggish, and the electrons are moving around it. So at any point, if you can think of the nuclei ground state, that is, if you can represent that, that constitutes the energy of the system. Now we can think of this in this manner. This is a very nice analog I got from internet. So here's a cow and flies surrounding it. If the nuclei are the cow, then the electrons are the flies. So that means whatever fast moving the cows might be, these flies can easily adjust it to its motion. That means it is very difficult for the cow to follow the fly's motion because the cow is massive, nucleus massive, but instantaneously these electrons can adjust it to the nucleus ground state. So this is the first approximation which came by von Oppenheimer. Now we were talking about initially one electron system, but in general, in reality, we know that every system has more electrons except hydrogen atom. And when you have to solve such an equation, we have to consider all the terms. That means we have to consider the kinetic energy of electrons, electron-nuclear interaction, electron-electron interaction, then the nuclear kinetic energy and the nuclear-nuclear interaction. Now, since we were telling in the previous slide that the nuclear moves little bit sluggish compared to the electrons, we can exclude these two terms and we can consider the first three terms which are more important energetically. So the kinetic energy of the electrons is a one body operator, very important. Electrons in the nuclear field, which is again a one body operator. Then we have electron-electron interactions, which is essentially the Coulombic repulsion, and which is a two body operator. So if we can solve these three terms, we can represent any system. So this is the expansion of it, the kinetic energy term, then the nuclear electron interaction term, and the electron-electron interaction term. How to solve this? Solving this is not easy, as I was continuously telling. So because we have this equation, and which is represented by the wave function. The wave function is actually a 3n dimensional quantity because the electronic wave function lives in the 3n dimensional space. Now we have to simplify it. So for example, to give an idea, if we have a simple iron atom that has 26 electrons, it will take 78 variables to describe this iron atom because you have to consider the space coordinates to specify the wave function. Okay, so the next approximation came. Okay, what will happen if we can include this atom in a box which has dimensions 10 along each direction, so that we still have 10 raised to 78 entries. That means one electron can take this many possibilities. Okay, so solving this is not an easy task. So even with the fastest supercomputer of which can do an exascale computer which can do only 10 raised to 18 operations per second. So we cannot directly go and solve this equation. So we have to have some more approximations included. So then comes the final density functional theory, which is basically having the von Oppenheimer approximation inside it, and which has these three terms which I was telling previously. So the approximation was this external correlation, that is the electron nuclei correlation, is actually a material specific quantity. Okay, so this is an external potential which is a function of 3 dimensions, which is a material specific quantity, but the wave function is 3n dimensional quantity. So we can approximate this term by an external potential, then we can calculate the wave function and energy from it. From that we can calculate the properties of the system. The final formulation is done by Hohenberg and Kohn. They approximated that, they actually proved that the ground state electron density take the role of this external correlation potential, so that if we can find the ground state density, which can determine the 3n dimensional ground state wave function energy. So the ground state energy is the main quantity which we are calculating. From that, all other properties can be calculated. This is the idea. I know that it's I'm telling many concepts in few slides, and there are much more into it rather than telling this, but this is just to give you an idea. This is how density functional theory was formulated, and these are the equations which is into it. Now this external potential exchange correlation function I was talking about, that external thing, this is the very important thing in calculation of, when you do a density functional theory calculation. That means if we know, essentially, if we know how the electrons and nuclei interact in a system, you can calculate almost every property of that. But it is very difficult to know because every system is different. That is how we have different elements in the periodic table. Okay, so to approximate it, we have to have again consider the nature of the system. For example, there were many approximations which came. The first one was local density approximation, and that means the electron density depends only it is very constant. It is locally, it is very constant. It is not varying very much. For such systems, LDA, this local density approximation, can be used. But there are systems where the electron density is varying drastically from point to point. Then we have to go for another approximation called generalized gradient approximation. Then we have there are systems which are strongly correlated with F electron systems, for example, rare earth elements. Then you cannot go for normal approximation. You need to go further above that. The point I'm trying to convey is, to treat different systems, we need to have different approximations taken into consideration, and these potentials are already developed. But if we have a universal potential, we can, you don't need to do different types of calculations. If you have a universal potential, you can universal exchange correlation functional, you can calculate every system, you can treat every system in the same manner. And this is actually equivalent to the Jacob's ladder. I think it's a biblical thing. So it's like it is a ladder to heaven. I don't have much idea, but I think, yeah, that's how it goes. So it is similar to that. When you have the LDA, you are in the lowest rung. Then we have the GGA, we climbed one more rung. Then we are climbing this ladder. If we have in the topmost rank, the complication is also increasing. And if we have one exchange correlation functional which can represent every system, then you have the highest chemical accuracy. Okay, this we have not yet reached there. So now we have to treat different systems differently, different materials differently, with different exchange correlation functionals. Those are some basic things. And now what DFT can do? DFT is a friendly, powerful tool that goes hand in hand with experiments. So we can calculate a lot of things like structural properties, magnetic, electrical, optical properties, and spectroscopics, and heat of formation. A lot of properties can be calculated. And here is this is a very nice graph from actually from Wikipedia. So you can see the fullerene molecule and how the electron density is plotted, calculated using DFT. And we can also calculate a lot of properties like heat of formation, etc. But even though we can calculate all these things, the main limitation, as I was telling, it is the lack of an exchange correlation universal functional. And certain systems, when you use DFT, you should be very careful. For example, Van der Waals monolayer or something, the treatment of dispersions, you should be very careful. And also there are underestimation of band gaps for strongly correlated systems. So you need to know what system you are using and what material is best suited for that. And when you compare with experiments, it's good to have a qualitative comparison rather than a quantitative comparison. For example, we calculate the band gap of some insulator as 3 eV in experiment. When you do DFT, maybe you can only do like 2.5, that much accuracy only maybe it's possible to achieve some cases. So this, you should be aware of that. But nevertheless, we can see the trends, how the trends are varying, how the electrons are interacting, all these things. So it's a ground state method, and yeah, we should be keeping that in mind when doing a DFT calculation. The ingredients of a DFT calculation is actually very simple. You need to know that what is your system. An example can be, for example, an iron, bulk iron. You want to calculate the magnetic moment of bulk iron, for example. So you need to know the structure, whether it is BCC or FCC, what is your structure, where are the atomic coordinates. So you need to know those things. And you need to also know like the plane wave energy cutoff. That means all these calculations are periodic calculations. So we need to know that how many block waves, plane waves are included in the calculation, all these things. And what are the accuracy in which you need your calculation should be performed, how much accurate you need. And all these calculations are performed in the Fourier space. So we need to know an idea of what are the reciprocal space length vectors, like the length of the reciprocal space vectors. Then finally, the pseudo potentials, that is one of the most important thing. This is the place where you say your program, how you are going to treat the valence and core electrons. So this is very important. You should also know you should know what is the system and what are you going to do. So these are the ingredients of a DFT calculation mainly. And here is a very nice graph which actually takes a picture which actually includes almost every exchange correlation functionals available currently. Now, I will show some examples where we have successfully used DFT to calculate material properties. The slides are selected in such a way that I will give an idea of purely theoretical, purely DFT calculations, and also how DFT was successfully used to compare and collaborate with experimental results. So in this slide, we have in our department, we also have a steel research center. And we had an experimental result which showed that in the TEM, high resolution TEM, the experimentalist observed a new phase of a steel, which is a hexagonal phase, which is not very common. And it is produced by the presence of some grain boundaries. And we have to analyze the stability of it. So to analyze the stability of it, we have calculated the phonon band structure, as you can see here. And the presence of this metastable phase is caused by the presence of interstitial carbon. So we simulated the system by iron, hexagonal iron with interstitial carbon, and also with many other alloying elements such as silicon, whatever is possibly in the, because the steel makers know what are the concentrations of alloying elements inside it. So we tried to reproduce that, and what we have seen here is, I just shown here two representative phonon band structures. When carbon is in the substitutional position in this structure, we could see that the phonon band structure is giving only positive frequencies. So if we have only positive frequencies, this structure is stable. But here you can see that when it is in the interstitial position, largely it is positive, but we can see that there is a negative mode coming in. So this structure is not stable. So using DFT, we can verify these kind of facts. We can study the phonon band structure and see whether it is stable or not. Now, this is another example in which we have used DFT to actually confirm some of our experimental results in our lab. So TiO2 clusters were synthesized, and they showed enhanced photocatalytic activity with doping. So we did DFT calculations on some very stable structures, TiO2 stable clusters, nanoclusters. And it is seen that the presence of silver is very beneficial for the hydrogen evolution reaction, and also it is modifying the band gap. On the right hand side, what the density of states is shown, and with this dopant, nickel and Ag dopant, there is a band structure changes happening, and there is also charge density difference, charge transfer occurring. So that is enhancing the activity of the TiO2 clusters. Now, it is also, initially in the first slide, I was showing actually a bulk material, bulk iron. In the second slide, I was showing a nano cluster. And here it is a perovskite material. I think in the previous talk also there was a mention of about photovoltaic perovskites and all. So there was experimental confirmations of this particular perovskite material, and they were showing a very nice uniform green emission, which was confirmed by PL. And then we used DFT to calculate the band gap, and then we also calculated the theoretical absorption, which was matching with the experimental data. And we successfully explained the phenomena like the charge transfer and band structure and all these things. And also the dielectric properties were calculated, which were also very much in agreement with the experiments. Now, hydrogen economy is in news all the time. And many materials are being used to capture hydrogen and split and store and everything. And we have also used, this is actually two different studies. In the left hand side, this one is a purely theoretical study where we used gallium nitride nanowires, which is semiconducting. Then we doped it with palladium and platinum, and then which was beneficial for hydrogen evolution, because when you attach hydrogen molecule to this bare nanowire, it stays as such as hydrogen molecule itself. But when we had this metallic addition, then there is an spontaneous splitting was happening. So you don't need to provide an energy to split it. So such kind of studies also can be performed using DFT, which can guide the experiments to give insight what can happen. Also, we have another similar study with the gallium nitride sensors, which was showing enhanced hydrogen detection, and which was the same geometry we have used, but in a different way. And we could show the, very good experiment confirmations, very good agreement with the experimental results. So DFT can be also used to study, as I was telling, a wide range of properties. This is one example in which we tried it with carbon dioxide attachment on the surface, and it is in that it is again the omega Fe surface, which I was telling in the initial slide. During steel production, actually a lot of carbon dioxide is being produced and the steel samples are being exposed. So there is a possibility that the carbon can attach, and also carbon dioxide getting in contact with the surface. So we used this omega Fe surfaces to see that whether it can capture carbon dioxide and whether it is it is undergoing any spontaneous splitting. And it is seen that, as you can see here, depends on where it is going to attach, the material is the molecule is getting activated, and also there is a possibility of spontaneous splitting as O and CO happening. So this is a very interesting study, and also we can, in these calculations, we can also see that whether there is an activation energy barrier, and we can calculate all these things using DFT studies. Now, there is also a lot of, actually we use this very routinely, but I'm just giving you a flavor of how we can compare with different materials. So this is a gallium nitride nanowires, again with doping, and in this study, experimentalist has seen that there is a significant change in properties occurring because of the presence of defects. But it is very difficult to confirm the presence of defects directly. So, but DFT can help there. So we can easily introduce defects in our calculations. So we have done with point defects and also complex defects such as dopant and point defect, and which has shown very high stability in the material. And also we could see that the electronic structure is altering. Now, coming to catalysis applications, a lot of noble metals surfaces are used for catalysis. And in this study, again, it is done with a collaboration with Tokyo Tech, Japan, and they were using this palladium catalyst, and then they have been alloying at the surface, which was enhancing the oxygen evolution reaction performance. And we could explain it, what is happening there, because we have to do a series of calculations to see where this carbon atom can go and absorb, and then how the electronic structure is changing. And there is a theory which shows that by Norskov, if the d band center is changing, it is favorable for catalytic reactions, and which was agreeing with the experimental results, and so we could successfully prove their results. And I was talking about structures, catalysis, and gas detection, etc. We can also do considerable studies on magnetism. So magnetic anisotropy is a phenomena by which, when the spins are oriented along two different directions in a material, we have to provide energy to change the spin orientation, to flip the spin. So such kind of materials are used in spintronic materials and magnetic storage media. So in this particular example, we studied two-dimensional neodymium nitride layers, and which showed very nice magnetic anisotropy with perpendicular anisotropy. And perpendicular anisotropy is more favorable for perpendicular magnetic storage devices. And this is a purely theoretical study, which can actually guide us a guide to experiments to attempt such kind of synthesis or further XMCD or magnetic dichroism, whatever studies they can do and verify it, and very much commercially also important materials these are. Now, hydrogen embrittlement, which is another very much important issue in steel making and also in many alloys, because during the production of these kind of alloys, structural alloys, many hydrogen can get in. So when it goes in, it will stay at some of the lattice sites or interstitial sites, and eventually it can degrade the material. So iron aluminide is a material which is used in many structural applications, and hydrogen embrittlement is a big problem there. And we try to find some of the some insights into it. The hydrogen, for example, there is already structural defects in the material called grain boundaries. So this hydrogen can go and stay there more easily than the bulk of the material. So in this study, we have checked. This is a grain boundary of FeAl without any defects. Then we introduced these defects, hydrogen, in many positions, and then calculated the formation energy and successfully explained the energy formation mechanisms here. This is actually a work of a bachelor thesis, and the student published a paper out of it. Very interesting, very simple but very powerful study. Now there are also everybody is aware of graphene. I think I mean we all hear a lot about graphene, which is the first successful 2D material, I think. And there are also many other 2D materials in nowadays being investigated for many properties. And one of them is Janus heterostructures. I'm sorry for the distorted figures. And this is basically MOS2 material, but one S layer is replaced by an SE layer. So in this structure, this kind of a structure is actually resembling the Roman god Janus, which has two-faceted god. So that's why it is named as Janus material. That means one in a two-dimensional chalcogenide material, one of the layers are replaced by another atom. So that's how that goes. So it is successfully synthesized, and a lot of studies are ongoing past few years, because these kind of materials are very much useful for many properties, catalysis, and also there is an intrinsic dipole moment because of this replacement of this atom. And these kind of properties can be tuned for many applications, and one of them is, of course, catalysis. For example, in these materials, hydrogen evolution reaction and oxygen evolution reaction can be achieved in the same material itself. So such possibilities are being investigated. So this is a purely theoretical study in which we try to actually do an interface calculation, because in reality, these are not freestanding materials. They have a substrate which are used to grow these materials. So we tried making interfaces with gallium arsenide, and these structures were very stable, and the electronic properties were drastically different, depends on the orientation of this material. So when you use gallium arsenide along with this, we can in fact get different properties depending on this orientation. As you can see here, MOSSE is having a considerable band gap, but when you have MOSES interfaced with gallium arsenide, you have a very continuous spectrum, continuous density of states. It's very metallic in nature. So these kind of properties can affect the further application of such kind of Janus materials. And this is just a representative example. Instead of MOSSE, many materials are being investigated, such as WSSE, PTSSE, and all. Yeah, this is a purely theoretical study, but there are also experiments which is coming out and very much happening in this area. So yeah, these are the things DFT can do, and I'm giving a very conclusive, very brief idea. We can also do a lot of things like non-metallic inclusions in steel. We can model nanoclusters, and also we can study the structural alloys, high entropy alloys, their mechanical stability. All this is, DFT can do, and independently as well as to support experiments, these kind of calculations. So this is another interesting study recently we published in Nature Communications, where the perovskite, actually this molecule is called PCBM, which is a very interesting molecule with a tail, fullerene with a tail of tail attached to it. And experimentalists have seen that when they have this kind of a geometry, this fullerene layer can act as a electron transporting layer, and they could successfully do a photo detector which can perform different logic gate operations by changing the polarity of light. So the basic thing is in a single photodetector, they can achieve different logic gate operations. Okay, so this is an experimental work mainly, but they have to understand why this is happening when they do this kind of a geometry, how this molecule is orienting, what is happening, the change in the electronic transport. And this is I supported this with DFT, and what we have seen is when this molecule is oriented in a certain way, for example, it is when oriented when the tail facing down towards this MAPI surface, then there is significant electronic states coming in the band gap, and which is helping the electronic transport property. Yeah, this is this kind of studies also can be, I mean, DFT can act as a very important tool to explain experimental phenomena and help the experimentalists to explain the results. So far I was telling about what DFT can do and what experiment is doing. Now there is also possible to do things which experiments cannot do. For example, the melting curve of iron, and which is, if you want to do such a thing, you cannot just go inside the inner core of Earth and do the experimental study. If you have to reproduce it, you have to maybe recreate the extreme situations of pressure and temperature, etc., by maybe using an atom bomb explosion or something like that. I was just vaguely telling, but yes, these kind of things which experiments cannot do very easily, but using DFT or ab initio modeling, we can in fact reproduce these curves, which can exactly reproduce the pressures, and which can be equated to the temperatures in such extreme situations. So these are some examples in which experiments are difficult to perform, but DFT can at least give a qualitative idea what can be the physical phenomena happening there. So these are the four paradigms. I would like to mention that DFT is not different from experiments, or it is not competing with experiments or anything. So these are all actually a paradigm means which is many things which are going together, which is benefiting each other and which is going together. So the first paradigm in science is something like the area, the times when people were doing experiments using fire and all. The initial period, maybe Michael Faraday's period. Yeah, I don't know exactly the years when he lived, but anyway, this is the first paradigm, is when people started curious about things and started doing experiments. Then the second paradigm is theoretical science evolved, and it was at its peak. All these physical phenomena were formulated using mathematics. Everything, Maxwell's equation, and these things came, but still these things didn't go extinct. It continued along with this. And then the third paradigm came in this period between 1950 to 2000. It was the golden area, when golden time. Then all this density functional theory, quantum mechanics, everything was like in a very clear form. Scientists were able to use quantum mechanics in a very clear form because of the advantages of computers and computing and everything. Then now it is the era of data-driven science, because it has to go hand in hand with experiment and density functional theory. So then, because DFT also generates a lot of data, and many times you may not know which is good data and which is bad data, there you can take the help of these kind of artificial intelligence or data science things. So science keep on evolving, and experiments, DFT and machine learning, all these things go hand in hand towards future. Maybe something else is in store. We yet don't know what is it, which is coming in the next maybe next few years or in future. So the future of DFT is like DFT will go hand in hand with machine learning. Each will depend each other a lot, and then a lot of phenomena will be predicted, and machine learning will be predicting something. Then we can verify it using DFT, feed it again, and this cycle goes on and on. So that's about everything I wanted to say, and I have some acknowledgements to make. I benefited a lot from listening to Nicola Marsari's videos, and I use CSEIT computing resources in Finland for all my computations, and I have quite a lot of experimental collaborators. I learn a lot from them, and also I will help them to explain their phenomena. That's all. Thank you.
Thank you, Asa, for very nice presentation regarding the DFT for condensed matter physics. And because we are running short of time, so I have a question. Have you done any work on the thermoelectric measurements by using DFT?
Yeah,
That studies
recently
because
we
yeah, some people are now
sorry.
very interested in that part on
Yeah,
vibration
yeah.
motions.
Recently we had a work. I didn't show it here, but I
Yeah.
was involved only very little in that. That's the reason I didn't show it. But we had recently a publication in thermoelectric properties.
Okay.
But
Thank
there you have to also
Yeah.
use some other post-processing tools such as bolt strap and such
Yeah.
things.
Yeah. I am
Yeah,
also doing some work on that.
yeah.
In this bootstrap I am using. That is why. Have you any idea? Then I can contact you. Okay. In this, if you
Yeah,
have.
let's see. Yeah, let's see. Because what I was involved in, it was in the DFT part, and someone else did the Bolstra
Yeah.
part. But we can think about it. It's not
Okay.
very difficult. Only thing is finding some suitable time.
Okay. Any questions? One question from audience, because we are running late, more than half an hour. Okay. Then thank you, Asaf, again for a very nice presentation on behalf of the organizers. Thank you once again. Thank you.
Thank you.
Now our next speaker is Libu Manjakal, who is talking on textile-based variable energy storage for autonomous system. Okay, now I'm giving a brief account of his biography. Libu Manjakal received BSc and MSc degree in physics from Calicut University and Mahatma Gandhi University in 2006 and 2008, respectively. He obtained PhD degree in electronic engineering from Institute of Electron Technology, ITE, Poland, in 2015 with Marie Curie Fellowship. From 2009 to 2012, he was with CMET Thrissur, India, and as a project staff. Prior to join PhD for short term, as he worked as a researcher in CENIMAT, School of Science and Technology, FCT Nova, Portugal. After completing PhD from 2015 to 2016, he was postdoctoral with ITE. In 2016, he joined University of Glasgow, UK, as a Marie Curie experienced researcher, and later he has been working as a research assistant in ESPRC project until 2018. Since 2018, he is research associate in same university. He is also working in the role of scientific project manager in a Marie Curie ITN project. He has co-authored more than 60 articles in the peer-reviewed journals with high impact. Libu's research achievements have been recognized by several credible agencies and institutes. He was shortlisted for important awards such as European Commission for Marie Curie Awards in Promising Research Talent category, Outstanding Young Scientist Scholarship Award from the Polish Ministry of Higher Education. BBC Science Focus magazine selected sweat-based supercapacitor work as one of the future technology to 22 ideas about to change our world. July 2020 and in 2018, the work on graphene form-based supercapacitor received Electra Award in the Best UK University Research category. As project investigator, he led collaborative project funding from Royal Academy of Engineering, NERC seed funding projects. He also involved as co-investigator in other projects. Now I invite Libu for his presentation.
Thank you so much, sir. Thank you so much for the detailed introduction. I'm happy to see you again.
Okay.
Yeah, we met long time back. I visited the university.
I know. Met during that period.
Yeah. I hope you can see my presentation.
Okay. Okay,
today,
so you can see.
Today, I would like to discuss with you one of my major work on textile-based wearable energy autonomous system for wearable application or healthcare monitoring applications. Before discussing about my energy storage devices, currently I am working as a scientific project manager in one of the Marie Curie ITN project called Aquasense. We have several partners from the Europe, including from Portugal, Serbia, Germany, Austria, Poland, UK, Ireland. We have total 15 PhD students working towards the central aim of monitoring the water quality by remote monitoring by using underwater robots or sensorized vehicles by deploying different type of sensors. So I am coordinating mainly the scientific part of the project after the completion of my PhD, and we built the consortium of this project. My major from 2012 onwards, during my PhD onwards, I am mainly working in electrochemical technologies. This is my work on PhD and energy storage devices during the postdoctoral period time. In sensors, I developed mainly the pH sensors for healthcare application and water quality monitoring, and also different type of glucose sensors and multi sensors for ion monitoring and conductivity or temperature sensors, and also physical sensors and gas sensors as well. I'm not discussing with today that in detail because of lack of the time. And here is the summary of the different type of pH sensors which I developed from 2012 onwards during my PhD and then postdoc. Initially, I started with, for example, in the water quality monitoring or food quality monitoring. Glass-based pH sensors have several limitations, including the chances of breaking and also the stability issues. To overcome that issue, I developed a potentiometric pH sensors in a thick film substrate, and initially on a rigid substrate, and then on LTCC technology, inbuilt sensor and reference electrode, and then wireless application. And later I developed the same sensors on interdigitator or a potentiometric sensors in a flexible substrate and a stretchable substrate, as well as textile-based sensors for several applications, including glucose health monitoring or a sweat monitoring application or a skin applications. Today's I would like to discuss more about the my work on energy storage devices. We know that in energy storage, it's a long applications or multiple applications in different areas. But my major aim is to convert that energy storage devices into a flexible version, mainly for a wearable application and also for autonomous systems. For example, we know that in a flexible energy storage have a different different chances of integrating, like in underwater vehicles or as a tag in animals in agriculture or also in healthcare applications. When we consider the progress of these multiple energy storage devices, we can see that there are different, depending on the application, like per hour or a 10 million. There are different applications.
Libu, your audio is muted, please.
Yes. Can you hear me now?
Okay.
So depending on the application or depending on the power range required for different devices, there is a progress in different areas, and also in technology status, there are small volume production, for example, in IoT or MEMS based sensors, and also there is a research going on in transport or robotics application, especially in a flexible version, because it is very difficult to obtain a high energy density energy storage devices in a flexible version. When we consider these flexible energy storage devices or a self-powered system, when we consider this flexible or a wearable energy storage system, then there must be a question like why we need a wearable energy or a wearable or a flexible energy storage devices. For example, you can see that there is a reported work on GAO from US, multiple sensors for a sweat monitoring. There are multi-sensors here, for example, pH sensors or glucose sensors or a lactin or a lactose or ion sensitive and sodium or potassium ions. All these sensors, some of them require power to operate. In addition to the sensors, there are a lot of electronics components as well, which requires power to operate these sensors. In addition to that, there is a sweat monitoring sensors for a single sensors like in online monitoring. We developed this sensor recently in sweat monitoring. For example, we developed a sensor on a stretchable substrate, and then also an antenna to operate that online application. These sensors are an electronic component required power. In addition to this, there are for a processes application, human machine interaction. Again, sensors like a physical sensors or a touch sensors required, which also required power to operate. So in this application, rigid-based energy storage devices have many limitations, especially in the curved surfaces. So there is a lot of studies going on in wearable energy or a flexible energy storage devices to operate these sensors. For example, there is a three category mainly energy harvesting. Different type of energy harvesters directly used as a energy to power the sensors like a triboelectric nanogenerators or a light energy like a flexible solar cells are there, and also thermoelectric energy devices. In addition to the energy harvesting, there are different type of energy storage devices like batteries or supercapacitors or hybrid batteries, and also this all on different substrate including flexible or a textile or a fiber-based energy storage devices. In addition to this energy storage or energy harvesters itself act as a sensor called self-powered electronic skin or which power the sensors act as a integrated devices. So these three categories are mainly used for a wearable application. We recently prepared a review article on this area. You can see the different type of self-powered systems used for a wearable application. Initially, when considered these systems, I started my work in energy storage on 2017 actually. I started with graphene-based energy storage devices for pH sensing to power the electrochemical sensor or a wearable sensors application. For example, previously I developed sensors, but my major difficulty is how to power these sensors for a continuous online monitoring. For example, in a daytime, we can use the solar cell or other energy harvesters. But in a sleeping time, how to monitor the sweat continuously? Then I started with developing a flexible version of energy storage. Initially started with a graphene sheet. But the problem of graphene sheet is that it is hydrophobic, but we need more electrolyte interaction and also more energy storage. Then I started to develop this energy storage on a graphene form. It's a 3D structure. So the major advantage is that it have more electrolyte interaction. And then you can see here that how the cross section, there is a substrate and then a graphene sheet act as a current collector instead of a platinum or other metal based current collector. I used the graphene. It gives me more flexibility. And then graphene form, and I used a phosphoric acid as an electrolyte in this one. You can see that it almost shows more than 25,000 cycles of charging, discharging. That means that many days it can operate. This is the advantage of supercapacitor. And then I integrated this supercapacitor, it's called a GFSC, graphene form based supercapacitor with a pH sensor. And then a solar cell. The solar cell generates the energy and it's stored in the graphene form based supercapacitor, and it used to power the chemiresistor based pH sensor. As you can see here, here on the hand we attached these devices, and in the daytime it can charge by using the solar cell and then store in the night, and then we can use continuously power the device. This work recognized as one of the best UK university category award providing by the industrial support. And then, but the major problem of this graphene form based supercapacitor that it have a limited energy density. I got nearly 3.4 microwatt energy per centimeter square energy. And so the application is limited. For example, like chemiresistor sensor with a low operating voltage or low current required, we can use that. But for a high power application or to operate a motors or to operate a actuator, I need more power. Then I started to prepare a new graphite polyurethane composite based supercapacitor. I prepared a new composite and then developed a flexible supercapacitor on a graphene sheet and a flexible PET substrate. And then you can see here that the cross section of this device, here the top polyurethane and the graphene sheet and the graphite polyurethane composite. And you can see that in a graphene, it shows a more hydrophobic, and then graphite polyurethane due to the rough surface It shows more hydrophilic nature. And then here again, I integrated this with a flexible solar cell, and depending on my power application, for example, to power a LED means 1.8 volt or something like that, 1 to 10 microwatt hour, I can use as a wristband. I convert this graphite polyurethane supercapacitor as a wristband, and then to operate again almost 84 LED it can operate, and 100 milliwatt power, for example, to operate a motor which required a voltage of 2.5 volt. I used this supercapacitor, and it is attached on the curved on the column here. You can see here this yellow color. And then finally, I integrated this supercapacitor on a prosthetic hand. For example, the motors in the each fingers required almost 5.6 voltage and almost 60 milliampere current. Then what I done that I integrated multiple supercapacitor and attached it on the hand and then covered with a solar cell. There is advanced version work is going on in this area to miniaturize the solar cell and also to improve the energy density of the device. Maybe I can show you some videos in this aspect. Here you can see that the flexibility, it shows the flexibility of the device. Here the supercapacitor attached on the to 3D printed cube, and you can see that it is bending, and I almost 24 mm. I done almost here 100 cycle, and again I continue this with more than 1000 cycles of cyclic bending, and it shows a stable performance. And also here you can see a solar cell charge the supercapacitor and then power the LED. Again, you can see that here the supercapacitor attached on the, you can see here that is the yellow one, and to power the motors. And it gives the short power. So that is a supercapacitor is giving an instantaneous power to the device. And finally, what we done that we attached the supercapacitor on the prosthetic hand and then power this fingers, and it can hold the object because of that there is a touch sensor we integrated. And later we further modified this and to hold any object. This gives the enough power to operate these devices. But the major problem of these energy storage devices, I noted that it uses phosphoric acid as an electrolyte. So when there is a break or any scratch or something like that, the electrolyte leakage is a critical problem in battery, and especially in a wearable application. So I was searching, how can I overcome this issue of electrolyte leakage? Then I found that there are multiple work on in energy autonomous or self-powered wearable system, like a non-sweat based energy devices like normal solar cell or triboelectric or a batteries and supercapacitor. This uses normal electrolyte or a normal materials and everything. But there is another category, sweat based energy devices. Mainly the work is going on biofuel cells, especially from Joseph Wang group in US. Mainly they developed multiple biofuel cells, and also there is a battery work going on again in US. Mainly used sweat as a chemical component to activate the electrodes. So during my work on sweat-based sensors, I noted that the sweat contain multiple ions like sodium or potassium or chlorine. Multiple ions are there, and also this is positive or cations and anions are there. So in a supercapacitor, we mainly look at an electrolyte as a NaCl or a KCl electrolyte. Why not we can use these ions as an electrolyte in energy storage devices? Then I came up with an idea about that. Develop a supercapacitor electrode which can absorb the sweat, and when we supply a voltage, it can use as an anion and cations. So, but in that case, I need a substrate which can easily absorb the electrolyte. Prior to that, you can see here the various biofuel cells, the growth in the biofuel cells. If you would like to see more, you can see the recently we published a review article in this area in advanced material. So when I'm coming with the sweat-based work, I need a substrate which can absorb the sweat, human sweat, very easily. So one of the most important, I found that our dress, our cloth. So I used it with a cellulose polyester cloth, and converted the cellulose polyester cloth to conductive substrate by using P.BSS. And then I applied the electrode on both sides of the substrate, and it can act as a device, you can see here that the cloth converted into a P.PSS conductive cloth. And then each fibers, I checked each fibers, how the P.PSS is distributed. And it is uniformly distributed on the surface of the electrode. And then when I applied a potential on these two cloth separated with another cloth, this cloth acts as a separator here. So what happened is that this separator I covered around the electrodes, and then when the separator wet by using sweat, and when I applied a potential, you can see here that the positive and negative ions due to this electrochemical double layer formation in previous talk questions are already explained about the electrochemical double layer and the pseudo capacitance reactions. What happened is that in P.PSS, it's a highly conductive material, and EDLC is formed on the surface of the electrode. As you can see here that in the Helmholtz layer or diffuse layer, and then further due to this conjugated polymer, I noted that during the electrochemical studies, there is a pseudo-capacitive reaction also happened on the redox reaction also happened on the inner part of this electrode. And then you can see here that the cross-section of this device here, here you can see there is a sweat and the substrate, the cloth, and then this small version, depending on the type of the device we required, we can increase the area of the device. Here you can see a small device. And then I compared this performance with the sweat equivalent electrolyte. I prepared a sweat equivalent electrolyte in our laboratory, and then I tested the device, and then I used a human sweat. We run in the treadmill or in a park, and we collected our own sweat on the cloth, and then used it as a electrolyte in the device. And when I compared this device, equivalent sweat equivalent electrolyte and with the human equivalent, it almost shows a 7 farad per gram capacitance, and it is enough to operate a small sensors. And then there will be a question about that different human or a different person have a different volume of sweat or our physical exercise. Then what I done that, and I found that it is purely depend on the volume of sweat and the area of the device. Then I compared different volume of set in impedance spectroscopic analysis and also CV analysis, also charging discharging. And you can see here that 20 microliter or a 20 sweat, and also 50 microliter and 100 microliter. And you can see here that in 100 microliter, depending on the size of the electrode, it shows almost a rectangular shape in performance and a high energy density area. In addition to this, our human sweat in a cloth can easily evaporate. Then what I done that I did a continuous cycle study, continuous initial performance, and you can see here that the initial cycle, the performances, charging, discharging is almost same. And then after 4,000 cycles, I saw a sudden drop in the potential value, and you can see here the variation. Then what I done that I opened the device and I checked the surface of the electrode to understand what happened the electrode surface. And then I noted that some of the material, because of the P.PSS, some of the material got disintegrate, and also there is a issue in the coating of the material, and the electrolyte is fully evaporated. Then what I done that I again dropped the sweat and then again studied, and I found that the device is working again, but not as like initial cycle. This is mainly due to the material degradation. So now currently I am looking forward a material which can long last with a high performances, and that work is going on. In addition to this, I also studied with different bending studies and a cyclic analysis. And you can see here that I integrated this textile based supercapacitor with a solar cell, and then as a salinity monitoring sensor to continuous monitoring our salinity, presence of the salinity level. And then here you can see that one of my colleague, we attached the device on the our t-shirt, and during exercise, we can see that the device got wet, and then it started the performances, live study we done. In addition to this, in another study with the human body, we directly attached this on the human body instead of the t-shirt. Yes. Here you can see that the wire coming out from the body. There is a sticker we put, and then we studied the performance of the device. And it shows that when we started the exercise, there is no sweat, and the potential, the capacitance was very, very low in nanofarad range. And once we started sweating, the device got wet and it started working, and it shows almost a millifarad range, microfarad range. Further to this, as you know that in future, there are different type of ions in the sweat or a different analytes in the sweat. And there are different sensors work also already reported. In addition to this, there are different type of biofuel cells and supercapacitors, and to operate the sweat-based energy autonomous system. Further, depending on the human physiological status, there may be a person who the sweat is very limited. So there is a work going on in reverse kinetophoresis method to extract the sweat. So, and to operate the different type of sensors. So there is a challenge, is the major challenge here, that different components require different type of power. For example, you can see here that sensors, pH, glucose, salinity, and also analog to digital converter, for example, the electronics part, required high voltage like a 3 volt, or a microcontroller required more voltage or more current. And in addition to this, there are human machine interaction. There are different type of sensors, and also wearable physical sensors are also there. These all devices or all electronics component required more power. But the presently fabricated biofuel cells or a supercapacitor or a battery based on sweat, I'm talking mainly about the sweat, are limited. So we need to find a new method or new solution to improve the energy storage devices or a capacity of the device, and based on the material engineering. And that work is currently going on, and I also working mainly focusing on this work. In addition to that, I also participate in another work with my colleague. We developed metal coated substrate as a textile as a substrate, and then fabricated supercapacitor to power the temperature sensor. And also we found that in another application, the flexible or a stretchable textile based supercapacitor itself acts as a sensor. For this, we fabricated a supercapacitor on a stretchable substrate, and then we studied different stretching and different releasing cycle from 0 to 40%, and we found that depending on the stretching, there is a change in the capacitance value. That means that the stretchable supercapacitor itself acts as a dual function role. It acts as an energy storage devices along with as a sensor. And currently, I am mainly focusing on this aspect, how to improve the performance of a single supercapacitor or a single energy storage devices for a multifunctional application to reduce the component of wearable systems. In addition to this, I also developed, because we know that in our country, there is a lot of normal natural fibers are there. What I done that during one of the collaborative work with in Royal Academy of Engineering with India, I developed a jute fiber converted as energy storage devices as a supercapacitor. You can see the project is mainly focused on a post-harvest loss monitoring to determine the quality of a food particle or a food package. So you can see here that I developed in a jute fiber, a single fiber, I converted into a conductive fiber by using P.PSS and a carbon nanotube. And then by multi-stacking this as a cable type supercapacitor developed. And then the same fiber act as a sensor as well. It's a temperature sensor or a humidity sensor. And then attached this fiber-based device on the food bag. And you can see here that, and when I started applying heat on this temperature sensor, the sensor got powered by using a supercapacitor here, and then charged by using solar cell. And this using for a self-powered bag or a package application. This all, I know there is a lack of time. I got a lot of supporting from the many funding agencies, and thank you so much. If you have any doubt, please.
Okay, thank you, Libo, for a very nice, very interesting talk on supercapacitors and their wearable applications, etc. One or two very quick questions from audience. No questions? Okay. If no questions, we can thank Libu for a very nice and interesting talk, and also in application level, he mentioned many things. I think that all the participants or audience will be very, very happy to know his findings and also application of new technology. Thank you. On behalf of the organizers, I thank Vibhu for his presentation. Thank you. Thank you once again.
Thank you so, thank you so much. Thank you so much.
Okay, now today's morning session, or we can say not morning, today half-day session, first and last one. Now we are moving to is presentation by Biju. Is the Professor V. Biju. He is from Department of Physics, University of Kerala, Karyavattam, Thiruvananthapuram. He is going to talk on storing energy at reduced graphite oxide water interface. Regarding his biography, Dr. Biju is the professor at Department of Physics, University of Kerala, Karyavattam. He obtained his PhD in physics from the University of Kerala in the year 2003 on the topic synthesis and characterization of nanostructured nickel oxide. He is also the director of Astronomical Observatory, University of Kerala, from 2017 onwards. He was one among the 20 young researchers chosen to attend the first advanced school of nanomaterial synthesis, characterization, and manipulation conducted by the department DST under Nano initiative of Department Government of India at JNCSR, Bangalore. He got exposure in the state-of-art analytical tools and procedures of nanomaterials. He has over 16 years of research experience and has over 30 publications in reputed SCI journals and has delivered invited lectures in several national and international conferences and has authored 8 book chapters. At present, 5 doctoral students were awarded PhD and 4 research students are working under him for doctorate degree. His research interests include nanostructured transition metal oxide synthesis and characterization, structure property correlation, reduced graphene oxide and activated carbon-based supercapacitors, pseudocapacitance and supercapacitors, nanomaterials and environmental applications, X-ray analysis of nanocrystalline materials, etc. With this introduction, I invite Dr. Professor Biju for his presentation.
Okay, thank you, Professor Progimnan. I think I'm audible and slides are also clear, isn't it?
Slides yet to come, but your audio is very clear.
Okay, sir.
Slides yet to come.
Is it clear now?
No, sir.
Sir, we can't see
You
slides.
please
Okay,
again. Once again, you.
okay, I will share it again. Now, okay?
No, sir. You just open your slide and then share screen.
Maybe let me leave the meeting and rejoin. It's not actually being shared.
Okay, pardon? I'm not able to hear you. What happened for sharing your screen? Any problem?
I'm not able to share actually.
No. I think for Zoom, initially you do one thing. You open your file and then.
Yes, it's open that way.
Yeah. Organizers, can you help him? Anybody is there?
Sir?
Yeah, okay.
The slide is visible now.
Okay.
Yeah,
okay.
yeah.
Okay,
Good,
let
sir.
me start.
Yeah,
Sorry for
full
the delay.
screen. Yeah, full screen. Mode you can continue.
Is it clear?
It is not in the full screen mode. Please change it to slide.
Okay, okay, slideshow. Is it okay now?
Okay, now.
Okay, sorry for the delay. Sorry for the delay. Thank you, Professor Pradimnan, and also organizers for the opportunity. So the title of the talk is Storing Energy at the Reduced Graphite Oxide Water Interface. Actually, this is about a supercapacitor which was constructed with reduced graphite oxide as the active material and water, actually pure water as the electrolyte, if you can call it as an electrolyte. So the idea is to present our experimental work on such a supercapacitor, which is also a multifunctional supercapacitor, which can actually harvest energy from heat energy. So I will not take 30 minutes. Probably I will finish it off in probably 20 minutes. Okay, sir, let me start. I know that you all have had introduction to supercapacitors, but I will just give a brief account of supercapacitors, what is required for our talk. Then I will just present the synthesis and characterization of RGO and the results on RGO pure water supercapacitor. And then we'll conclude. Now, as an introduction, what I have to say is that capacitors are energy storage devices, just like batteries. But there are some differences between batteries and capacitors. In fact, in batteries, energy is stored indirectly or in a chemical way. And during the charging or discharging, there is chemical change that happens in the battery. Again, due to the chemical changes that occur, and since these chemical reactions are not perfectly reversible, every battery, the cycle life is restricted. And again, since a chemical reaction is involved, charging and discharging of batteries are rather slow. Now, batteries have high energy densities, which means that it can store large quantities of energy compared to capacitors, and its power density is rather less. Power density means that the transfer of energy, the rate at which energy can be transferred is rather less compared to capacitors. Now, the ordinary capacitors that we use for electronic circuits are the ones which store energy in a physical manner. In fact, in ordinary capacitors, energy storage is in an electrostatic way. Since there is a charge separation, positive and negative charges are separated by a dielectric medium, there is no chemistry involved. It's purely a physical process. And since no chemical changes are involved, the device can be charged very fast, and discharging is also quite fast. That is why when you want to have an oscillator, you can use a capacitor in an electronic circuit. And it can be charged and discharged any number of times, practically infinite number of times, without any degradation in the performance. Now, supercapacitors actually fall in between that of capacitors and batteries, where the power density of supercapacitors is much larger compared to batteries, whereas the energy density is much larger than electrolytic or ordinary capacitors. That is where supercapacitors fall. Maybe you can say that a supercapacitor is something like, if you can say water is energy, then supercapacitor is something like water stored in a glass on your table, which you can very fastly fill and equally fastly you can use it up. Whereas maybe batteries is something like maybe water on your in a dam, or water in maybe a overhead tank, where unlimited supply of water is available, but drawing water from it requires some time. So this is practically an analogy between batteries and capacitors. And again, what you can say that suppose if you are a marathon runner, you need energy for a long period of time. You need a battery to work for you. Whereas if you are an Usain Bolt who runs 100 meters or 200 meters, then you need large quantity of energy in a very small interval of time, or your power requirement is high. So for a marathon runner, you need a battery, whereas for a spurt of energy, like in a 100-meter dash, what you require is a supercapacitor. So practically for most of the portable electronic devices, as well as applications such as electrically driven vehicles, we require both batteries and capacitors, supercapacitors, because there are requirements of energy where you need a sustainable supply of energy, you require battery. Whereas if you require only a small quantity of energy, but it has to be drawn at a very rapid rate, you require a supercapacitor. I hope it is very clear. Now, the second slide is a more scientific thing where we draw power density along the y-axis and energy density along the x-axis, and various energy storage devices are also shown the regions where ordinary capacitors have very high power densities with very low energy densities. Batteries and fuel cells have very high energy densities with low power densities, and supercapacitors actually fall in between them. And the cycle lives of supercapacitors is also very large compared to that of batteries. Now, the basic construction and mechanism of energy storage in a supercapacitor is very similar to that of a battery. That is, you have a positive electrode, a negative electrode, an electrolyte in between, and a separator which does not allow electronic contact between the electrodes, but rather allows the ions to pass through. This is the basic construction of a supercapacitor, which is rather similar to that of a rechargeable battery. Now, here the energy is stored. Either there are different energy storage mechanisms, and the three major energy storage mechanisms that we have to discuss are the electric double layer mechanism, pseudo-capacitor mechanism, and intercalation pseudo-capacitors. Now, the first one is the most conventional supercapacitor, where the energy is stored between the electrolyte and an active material. And here, when you apply a positive charge to an electrode, in fact, the electrons of the anions of the electrolyte will form a very thin layer very close to the electrode material, and if your electrode material has very high surface area, a double layer is produced where the active material contains positive charges and the electrolyte layer contains negative charges, and they are separated by a very small distance. This is what is called a double layer. As you know, this is very similar to that of an ordinary capacitor, and since the area of the active material is very large and the distance of separation between these two layers is very small, a very large capacitance is achieved. This is the ordinary EDLC, or the electric double layer capacitor, which is the most conventional supercapacitor. Now, the second thing is pseudo-capacitor, which is something very similar to batteries, where there is a charge transfer between the active material and the electrolyte. So it is called a pseudo-capacitor, where the capacitance that we can achieve, actually this is mimicking an this is mimicking the capacitor action. There is some charge transfer, Faraday charge transfer involved, and such capacitors actually have much higher capacitance than electric double layer capacitors. Now there is a third class which is called the intercalation supercapacitor, which works in a manner which is very similar to that of a lithium intercalation battery, where the intercalation of ions within the layers of active materials happen, and it is the capacitance have some advantages when compared to conventional EDLC and pseudo capacitors. These are the three mechanisms. We need these mechanisms to discuss our work. That is why we have spent some time on it. Now let us see what is reduced graphite oxide and how it is produced. Now we are all familiar with the graphene, and reduced graphite oxide is something which we can call as modified graphene. In fact, it is very similar to graphene, but differs in the fact that it contains many functional groups, especially oxygen functional groups like COOH or COOH, attached to a graphene layer. And in most of the cases, you will have multiple layers of graphene with these oxygen functional groups attached. That is what we call as reduced graphite oxide. Now, this graphene and reduced graphite oxide have been used as active materials in supercapacitors with the different electrolytes. A list is shown here. You can see that H2SO4, then KOH, all these things have been used as electrolytes, whereas graphite oxide and reduced graphite oxide are used as the active materials. And you get specific capacitance values. Specific capacitance means capacitance you could obtain per unit mass of the active material. It falls in a wide range, starting from 6 farad per gram to as high as 230 farad per gram. And this list is not complete actually. You can have still higher values of specific capacitance using reduced graphite oxide as an active material and a suitable electrolyte. Now this list contains only aqueous electrolytes, and there are works in which other electrolytes, organic electrolytes, are also employed. Now, in this work, what we have done is we have used a properly synthesized, a systematically reduced graphite oxide or graphene oxide as an active material, and we have used the pure water, actually HPLC grade water, as an electrolyte, and the effect of reduction of graphite oxide on the supercapacitor action is studied. Now, this graphite oxide has advantages such as it is a very cost-effective material and it can be scalable. The synthesis can be scalable to very high volume production is possible. And since solution-based approaches are used, you do not need very sophisticated techniques for the fabrication of the active material. Now let us see the synthesis that we have followed. We have followed the conventional modified Hammer's method for the synthesis of graphite oxide. First, graphite oxide means you have graphite layers which are exfoliated and then which are first oxidized and then exfoliated. That is the precursor material for the synthesis of reduced graphite oxide. Now we have used the conventional modified Hammer's method. It is a very common method where the details can be found in literature. And then we have reduced this graphite oxide using hydrogen hydrate as a reducing agent. So it was an aqueous solution-based reducing technique to obtain reduced graphite oxide. Now we changed the time of the reaction to obtain different levels of reduction for graphite oxide. So 0, it was the reduction time, 0 was the starting material, and the reduction time was changed from half an hour to 12 hours. And the sample codes are 0.5 means reduced for 30 minutes, then 1 means 1 hour, 2 hour, 6 hour, and 12 hour, and so on. Now this graph shows, this slide shows the XRD pattern of the graphite sample, graphite oxide sample, and the reduced graphite oxide samples for different time intervals. You can see that for graphite oxide, due to the intercalation of oxygen functionalities, the 002 layer of 002 peak of graphite has shifted to lower 2 theta angles, which means higher d values. And when you reduce, the peak comes back to almost the original position of the graphite. But you can note that the peak has broadened much. And actually this broadening has happened due to the fact that when these layers are restocked, they are stocked in a disordered manner. In fact, this blue diagram shows a typical graphite structure, whereas the bottom one shows what we have obtained, which is called a turbostratic structure. As an analogy, we have shown here a graphite layers, something like books which are properly arranged, where the layers are all in the same orientation. Whereas in the bottom figure, you can see the turbostratic structure, where if books are arranged like this, you can see that a particular set of d values are here, then a particular set of d values in other orientation, and so on. That is what we have obtained from our XRD. So we have deconvoluted the XRD, then obtained the different d values present, and also estimated the number of layers with each d value. All these are summarized. These details you can find from literature, and these are the d values as well as the number of layers with each d values that we have obtained for the RGO samples. Let us concentrate on RGO 0.5, which have different d values and also different number of layers for each. That is the sample that we are going to analyze. And we also did the transmission electron microscopy studies. The high resolution transmission electron microscopy studies also supported the XRD results that it is turbostratic in nature. Now, the SEM analysis also was done, which showed again the layered structure of RGO. Now, specific surface area measurements were also done. Now, the specific surface area of samples that we obtained were of the range of 35.47 meters per gram for RGO 0.5. These values were not very high nor very low. Now, the Raman spectroscopy is one of the techniques that is conventionally used to study the defect structure of RGO and graphene. And we also did it and found that when we reduce graphene oxide chemically using hydrazine hydrate, the ID by IG value gradually increases. In fact, ID by IG value is a measure of presence of defects in RGO, and naturally when we reduce, there are some breaking that happens in the layers, some pores are generated, and that is what leads to the higher defect concentration in these samples. Again, IR results were also done, which also supported the reduction due to hydrazine hydrate. Now, we also did the TGA studies and combined them with CHNSO analysis to obtain the chemical composition of our RGO samples, which are listed here. So our RGO geo sample, it was something like C5.74, H5.26416 with a water content of 18.82 weight percentage. And as we reduced, the C by O ratio increased, the C by H ratio increased. There was some nitrogen incorporated since hydrazine hydrate contained nitrogen, and C by N ratio also increased, and again the water content actually decreased. Now we did the XPS analysis to see what are the oxygen functionalities present as well as to quantify different oxygen functionalities present. So these are the carbon XPS of all the samples, and the results are summarized. See, the GEO as well as all other samples contain OH, CO, C double bond O, and C the OOH other than the carbon-carbon single and double bonds. Now let us concentrate only on one point, that is the concentration or the atomic percentage of OH. GEO contain the OH is only 1.15%, whereas as the reduction proceeded, the OH content actually increased suddenly to 75.97%. So if the oxygen functionality is present in RGO 0.5, the oxygen OH group was 75.97%, and then it gradually decreased. In fact, DFT studies have shown that when GO is reduced by the chemical reaction with hydrogen hydrate, see the CO groups, the epoxide groups which are present in the interior of the graphene layers, actually they are first hydroxized, they are hydrolyzed to form COH, and then they are converted to other carbonyl groups. So this actually supports the very high percentage of COH in the sample which was reduced for a very short interval of time, 30 minutes. You can see in this graph that the GEO sample contained a large quantity of CO bond, whereas COH is very small. But at 30 minutes, we have very high percentage of COH, whereas other groups decreases. And as time proceeded, these COH groups were being converted to again COH and C single bond O groups. Now this is very crucial in the performance of the supercapacitor, the very high concentration of COH. Now the specific resistance of these samples were also measured, and as expected during reduction, the specific resistance gradually decreased because the graphitic layers were actually becoming more and more. Now, the supercapacitor electrodes were produced in the very conventional way. The images are shown. And I will skip the characterization techniques for supercapacitors. We have to use the galvanostatic charge discharge, then cyclic voltammetry, as well as impedance spectroscopy to characterize the supercapacitors. The details I will just skip. And I will just go to the result and show the result. See, one can see on the left-hand side the cyclic voltammograms of RGO pure water supercapacitor at the different scan rates starting from 10 millivolt per second to 500 millivolt per second. In fact, the energy stored, the area enclosed by the curve can be considered as a measure of the energy stored by the device. Now, on the RHS, we are actually showing the performance of different combinations. The yellow one shows the coins, which means the electrodes, the metal current collectors along with a dry filter paper. You can see that practically no energy is stored, as the energy enclosed is energy stored is practically zero. And when the coins and a wet filter paper is there, even when there is no energy, the black color histogram on the right hand side practically encloses no area. The third one is RGO 0.5 and dry filter paper. So you have the active material, you have the separator, which is the filter paper, but there is no water present. Then also practically no energy is stored. But when the filter paper is wet, you have some area, which means energy is stored in the device. So this is the result that we obtained. Now, we repeated this experiment a number of times with the different types of water: ordinary water, distilled water, double distilled water, deionized water, doubly deionized water, and of course pure HPLC water. And in all those cases, we got similar result that we can store energy at the RGO water interface. And in order to obtain the specific capacitance, the charge discharging experiment was done. And you can see that at 0.3 ampere per gram, the charge storage is there and the discharge curve is also there, from which we could obtain the specific capacitance. The specific capacitance at 0.3 ampere per gram is very high, actually. It is 333 farad per gram. And even at 1 ampere per gram, you have some capacitance like 5 farad per gram is there. The energy density and power density values were also estimated, and these values are not very high when you compare it with a supercapacitor that actually uses an electrolyte, because for applications, the previous speaker, Professor Libu, actually was presenting about micro supercapacitors where the power requirements was rather low. But if you want to use supercapacitors for maybe some other applications, the what is expected, the capacitance expected is in very high current ranges. So at that very high current ranges, our specific capacitance and energy density and power density are not that much high. But when you come to in the range of 0.3 ampere per gram or 0.4 ampere per gram, you have specific capacitance which is not negligible. Now the other part, now what we are going to do is to analyze what is the energy storage mechanism. See, if the energy storage is in electric double layer, you will get a what you call as a square curve in something like a box type serial diagram. But what we have obtained is not a box type one. So we did an analysis, the details of which I am skipping. It showed that the energy storage mechanism is actually an intercalation of electrons. It is not just a surface-based energy storage mechanism. In fact, EDLC as well as the pseudo-capacitive reaction that happens are surface-related mechanism, where the B value in this particular curve where we are plotting log current density versus log rate of charge from the cyclic voltogram, the B value should be closer to 1. But we are getting a B value which is closer to 0.5, which shows that the energy storage mechanism is an intercalation or a battery type thing. So we hypothesized the mechanism for energy storage like this, because OH, the hydroxyl groups, when it is attached to RGO, it can, in presence of water, actually it can produce hydroxyl radicals, that is H3O plus ions can be produced by OH groups in presence of water. So DFT studies have actually proposed such a mechanism, and if that mechanism is true, then our active materials should have a negative pseudo potential. That is, when it should actually have a negative charge, and then if H3O ions are produced in water, then it should actually form a double layer. And on the electrolyte side, on the water side, you have H3O plus, and on the surface of the active material, you should have a negative charges. So we measured the zeta potential of a dispersion of our active material in water, and we obtained a minus 20.7 millivolt, and the pH of the solution was 5.67. So the pH of the solution negative means you have presence of H3O plus when you disperse this reduce the graphene oxide in water. So H3O, our hypothesis that H3O plus ions are produced in water in presence of our active material, you have some proof from this experiment. Now, this hydroxyl groups is abundant due to the very high concentration of OH ions in our RGO material. And in fact, these hydroxyl radicals can actually intercalate within these RGO layers to store energy. Now, if this mechanism that we propose is true, then we thought that if we can create a temperature gradient between two similar electrodes, then these ions should actually migrate to the colder junction, which in fact should actually self-charge this supercapacitor. So if our hypothesis that the mechanism of energy storage that we propose at the RGO water interface is true, then we should be able to thermally self-charge this supercapacitor. Again, before that, we also did one more experiment. That is, when this material was dry, you have a particular resistance value. But if you hydrate this, if you add some water, the resistance suddenly decreased many folds. And then if the material is allowed to dry, it actually regained the original resistance value. So this also supported our hypothesis that when our RGO material is in contact with water, these ions, these H3O plus ions are produced. Again, let's skip this, and we actually measured the diffusion coefficient of it also, and the diffusion coefficient had a considerable value. Now, when this supercapacitor was charged again and again, we found that after about 100 cycles, the value of the capacitance decreased. But when we wet the supercapacitor again, what we obtained is again a regaining of charge. Actually, the charge, its capacitance actually was more than 100% compared to the previous value when it was wet, and again it gradually, as the water was getting dried, the supercapacitance value gradually decreased. Now, this is the experiment that we did with a hot plate with one hot electrode and the other cold electrode, and our active material in between, with HPLC water, and we could see that we could self-charge this supercapacitor. The curve is shown here, the voltage generated is here, and the temperature of the hot junction, it was changed up to 80 degrees. Since it is water, we couldn't go higher, and since these two electrodes were very close, the cold electrode was also getting heated up, but the temperature changed only up to 48 degrees Celsius when the hot electrode temperature was 80 degrees Celsius, and we could see that the voltage, thermal voltage generated is not negligible. It was actually up to, we could get up to something like the 150 millivolt per degree Celsius of this change. So the voltage generated is 4.54 millivolt per degree Celsius, which was rather good when you compare with the other thermally self-charging supercapacitors reported in the literature. So we did with the other samples also, where the OH concentration was less compared to this particular sample, and we obtained that result that when there was considerable OH percentage concentration, we could store energy, but the performance was best for the sample which we discussed the first, and the behavior was similar in all the cases. The only thing was the specific capacitance was maximum for 0.5 sample, which contained the largest quantity of OH ions attached to the graphene layers. Then the mechanism in all these cases were studied, and it was found that in that particular sample, in all the scan rates, the intercalation was happening, but for the other samples, only at the higher scan rates intercalation was there, whereas in lower scan rates, the surface-based mechanisms like this double layer and pseudo capacitance were dominating factors. So basically, this is the work, and so what we did was storing energy at RGO water interface. So we thought that using water, because we do have, if you could scale up this thing, we can have harvesting of thermal energy and storing it in a supercapacitor without using any electrolyte and having the storage at the RGO water interface. Now, this could also have some applications in wearable devices and portable electronic devices where you do not need any acidic or basic electrolytes, which are conventionally used for energy storage. So this is the work done. Actually, this was part of a PhD thesis of Dr. Pingu Krishnan, who is presently working as assistant professor in Government College, Chavara. And I do thank my research group, University of Kerala, and all the listeners, and Professor Pradyuman for the opportunity. Thank you, sir.
Okay, thank you, Professor Biju, for very, very informative talk. Any one or two quick questions from audience? Because anyway, we are late, but he converted in time for lesser time. Any queries or questions? One or two quick questions, and we can move to poster session. Okay, thank you. Then no more questions.
Okay,
Yeah.
thank you.
Thank you, Professor Biju, for a very nice. Okay, and also once again, on behalf of the organizing committee, I thank all the speakers in this session. Thank you once again.
Okay, thank you, sir.
Thank you, sir.
Yeah.
Our first session has come to an end. A heartfelt thank you to our chair, Professor Pradyumnan PP, for conducting the session. I would like to thank all our speakers, Professor Aldrin Anthony, Professor R. Prashant, Professor S. Asha Ramin, Dr. Libu Manchakal, Professor Bijuvi, for the remarkably comprehensive and fascinating manner in which they have shared their knowledge with us. I also extend my gratitude to all the viewers for their active participation. A great thank you to all. A feedback form is available on the chat box. We request you all to fill the form before moving on to the poster session. Right now, we will have the poster session on energy materials. In order to attend the poster session, please visit the conference website or follow the link that will be available on the chat box. Poster presenters, please note that an expert committee will be reviewing all the posters displayed on the website. After the poster session, we will move on to the second session of the day, which will start at 2 p.m. You can join the session using the same link. Thank you all and good afternoon.